All right, so we finished up chapter 2 talking about the TCP/IP model. So pretty cool stuff, right? You're going to notice that chapter 1, chapter 2, chapter 3, and maybe chapter 4. Let's see, let's take a look at chapter 4. I mean, why say maybe? And chapter 4 are going to be a lot of concepts. This is normal with the CCNA. Do not get an idea that your entire time is going to be theory. Unfortunately, the part of the course has to start off this way because there's lots of things that we need to understand. You know, when we put on an IP address, there's things happening in the background. The second we do a no shut on that interface, things happen. So it's best to know what's happening in the background. We can't really troubleshoot something if we don't really understand what we're trying to accomplish when we do it. So there's a lot of theory in the beginning. And even when we get into starting to configure the routers and stuff like that and the switches, you start to realize that there's still theory with it, but it's kind of a 50-50 thing going on. You're spending a lot of time on the equipment, but you're also going back to go through those theories and so on and so on. But nonetheless, TCP/IP is a suite. It's a stack of protocols. It's a mixture of IP protocol and TCP protocol. So what we talked about earlier was the fact that when we were going through the OSI model, how TCP was guaranteed and UDP was not guaranteed, was just best effort. And up here you can see it says TCP is a protocol stack used for communication between nodes. Now, it's not the only protocol out there that can be used to communicate between nodes. And what are nodes? That's right, nodes are PCs, just like we were talking about before. And TCP is the concept of having guaranteed delivery, which means whoever you're communicating with, they're going to be communicating behind the scenes along with the transformation of the data to make sure that each one is getting each piece of data. So let's take a look at PC1 here and PC2. As PC1 is sending data over to PC2, PC2 is going to receive that data coming in on its interface, and then PC2 is going to send a message back saying, hey dude, I got it. And that's just pretty much it. And they'll keep going back and forth for every piece of data that they keep sending to each other. They're going to acknowledge that they got that piece of data. And this is how this guaranteed delivery works. Now, UDP is pretty much PC1 is going to take the information and send it out of this interface, and he's not expecting anything back. Now remember the important aspect of the OSI model. What's really the main key factor of why we learn the OSI model? Yes, we learn it as a means of learning how to communicate and so on and so on. But the main thing that we're learning here is the building of the headers. That's really the most crucial aspect. As the PC1 is building something or is trying to send data, he's going to build that information. Now, what does that mean? That means I'm going to have my data here. Here's my data. If I have port information, my layer 4 goes here. That might, we'll say just port 33. Just pick whatever port number. On top of that, that layer 3 header is going to have the source IP and the destination IP. And then on top of this, the layer 2 is going to have its header information. And it's going to have the source MAC and the destination MAC. Now, when we put something in front of the real data, we like to call the data the payload. This is a term I don't use often as far as the course is concerned, or just in general. I feel that communicating with you or anyone, there's certain words that I use and I don't try to use those words. just because I'm teaching. But the payload is just whatever you're sending. To me, that's just data. I mean, all of this is data, but the bottom line is when I have this setup here, the data will be the payload. The payload is what we're trying to get, the real information we're trying to get from PC1 to PC2. We have to understand that once the data has information in front of it, which you have to understand this as well, the data has to have something in front of it. Because if this information is in here, like I showed you in the OSI model, the data is not going to go anywhere anyway. If we did not have source and destination IP addresses, source and destination MAC, the data just won't go anywhere. If PC2 received this data coming in here with no other information, PC2 is going to say, well, okay, but I have no idea if that's for me, so I don't really care about it. Only when PC2 sees that the information is for him, he will accept that information. Now, it's still coming into the network card. Don't get me wrong. It's not like if you just block all this data and you're not going to be eating up the bandwidth of your network card. Now, when I say the bandwidth, really we're talking about the bandwidth of the network card as it's going across the wire. The network card has its bandwidth itself, but I'm talking about as the wire is coming in. I mean, as the data is coming across the wire. So, if we have a bandwidth of 100 megabits per second, and this is being filled up with data and your bandwidth is maxed, they might be dropping 90% of the data that's coming in there, but the bandwidth is still used. Does that make sense? I mean, it still has to get there in order for it to get dropped. And you can think of it as a traffic jam. You got thousands of cars going on this one highway, and only 10% of that is allowed to go through. Well, the traffic is still backed up. Your bandwidth is still used. So, because of this, we need this information in order to figure out where it's going and figuring out if that data belongs to me. Now, when we put something in front of a data, we call it encapsulation. We call it this because of the fact that the second I put a layer 4 information on here, I can't see the data anymore. This is all I can see. Once I put layer 3 information on here, I'm not looking at the layer 4 or the data. I'm looking at this. Once I put this layer 2 information on here, I'm not looking at the layer 3 information. I'm looking at the layer 2. The reason why we call it encapsulation, look at it like this. It's encapsulated because you're not going to pay attention to layer 3 or 4 or data. You don't know what's behind there until you decide from the layer 2's perspective, the layer 2 header, that this belongs to you. So if this is going to a destination MAC address of AAAA, and this PC down here, MAC address is BBBB, when that data comes into this network card, PC1 is going to look at it and say, well, wait a minute. I'm looking at the destination MAC here of the layer 2 information, the layer 2 header, and it doesn't belong to me. Well, if it doesn't belong to me, what am I going to do with it? I'm going to drop it. I'm not even why would I go any further? That's the concept of encapsulation. We have taken the data and we have encapsulated that data with layer 4 information. Now, if we encapsulated that with layer 4 information, now we have this data that's literally is going to be encapsulated by layer 3 information. And if that's the case, then we're going to have this data that's encapsulated by layer 2 information. And then, of course, this whole piece of data is what's going to go into the PC. Now, if the PC2 sees that the destination is BBBB, then PC1 will say, oh, well, that's my MAC address. It's for me. So I'm going to go ahead and strip off the layer 2 information, look at layer 3. Then I'm going to look at the what? Destination MAC address. I'm sorry, destination IP address. And if that destination IP address belongs to me, then I will strip that off and look at the layer 4 information. So anyway down the line, this data will be lost or dropped if it doesn't belong to them. So what does this mean? With TCP, we are sending all this data back and forth and guaranteeing the data. However, with UDP, that data gets sent out, which means I'm going to take my data, I'm going to build my layer 3 information, I'm going to build my layer 2 information. Yeah, we didn't have layer 4 in there in that time. Remember, if we're not going to use the information, there's nothing to put in there, right? And we're going to just send this out the interface. Now, because PC1, or PC2, sorry, because PC2 is connected on the other side of this link, he will get that information. But PC1 has no idea if PC2 got it. I mean, this wire could go somewhere else. PC1 doesn't know. I mean, what if PC1 was sitting on a switch? If PC1 was sitting on a switch, and so was PC2, PC1 just knows he sends it out. That's it. He has no idea he's connected to a switch, nor does he care. He just knows that he has an uplink, and that's the active interface that data needs to go out of. That's all he knows, and that's all he cares about. So UDP we like to call best effort delivery. There's no guarantee. Now, the real lesson of this, though, is really what TCP does. Now, we saw this before looking at the TCP IP protocol suite. And when we look at this and we compare it to the actual OSI model, we got the data link sitting here. We got the network sitting here. Let's move this over here. We got the data link. We got the network, and we got the transport. Now, at the transport layer of the OSI model is where TCP and UDP sits for our TCP IP protocol suite. Now, remember, this is a suite of protocols. This is not a model that we're looking at here. This is actually the TCP IP protocol suite. So, of course, this portion, these protocols of the TCP IP suite, the TCP and UDP, is just showing you what layer of the OSI model it works at. And it's going to be the transport layer. Now, based on that, let's find out how TCP initiates and starts communication between two PCs. When PC1 wants to set up a TCP communication, which means if an application like Firefox decides that he wants to, he, she, or it, that Firefox itself wants to set up or get some data from a web server. Now, once this happens, before data can really come from PC 1 and 2, we have to have a TCP three-way handshake established first. Now, this is very important to understand because the real data is what Firefox is going to be receiving from the server. If that's the case, I need to have this method of setting up communication first before I get any data, which means if we cannot get through the three-way handshake first, we would never be able to start sending data. And what's the three-way handshake? Well, we have two types. We have two types of systems we're dealing here: the client and the server. So in a TCP session, whoever initiates the actual communication, they're going to send out what is called a sing message. S-Y-N, I might have said it wrong, but send message, sorry. I just said sing, but send message. Now this send message is saying, I'm trying to synchronize with you. And because PC1 is the one who sent out the original send message, he becomes the TCP client. And the person he's trying, whoever is receiving this send message, which is the PC that PC1 is trying to communicate with becomes a server. All because this dude initiated it. So he's the client. So now he becomes a server. Now, when this send message goes over to PC2, PC2 is going to receive it. He's going to look at that send message. Now, remember, everyone, there's certain, when we're communicating, there's certain information that we have to have. Remember, we might be sending out a send message, but this is still a message. It's still data. So what else do we still need in there? Well, we need the layer 3 information, source and destination IP. You're going to have those headers on there, and you're going to have the layer 2, source and MAC address in this message somewhere. Now, if you looked at Wireshark, you would definitely see it. You will see the TCP information sitting here, and you will see the layer 3 information, the layer 2 information. So remember, this is how PCs are getting the data, the information that they need, all from the headers. So the concept of getting this three-way communication means that what we're trying to establish from both PCs' perspective is the fact that each PC knows that two-way communication is possible. Now, this only guarantees two-way communication at that moment, but still nonetheless. So PC1 sends out a message, goes out of his network card, and it's a send message. The layer 3 information will get that information over to PC1. Now, when I say the layer 3 information, we're talking about the layer 3 information that has encapsulated the data itself. In this layer 3 header, we're going to have the destination IP address, or where we want to go to. So this send message is now our data, so to speak, and that send message is coming over to here, to PC2. Now, when PC2 gets this information, what has this proved at this point? Nothing. The send message actually comes into PC2. All this means is that PC1 has received information. From PC1's perspective, he has no idea if that PC has gotten it. From PC2's perspective, he knows at least data is coming from that PC. So at that point, he would know one-way communication is possible, and that one-way communication would be from PC1 to PC2. So what PC2 is going to do is send out another message over to PC1, saying, I got your sync message, and here's my acknowledgement of that sync message. Now, this is interesting because what this proves at this point, PC1 knows he sent a message out, and he knows he got a message back from that person he sent it to. So now PC2 knows two-way communication is possible. He knows this, but PC2 doesn't. All PC2 knows is that he got data from the source and sent data to the source. He has no idea that PC1 got the acknowledgement that he sent out. So now, because of that, that's where the third handshake comes into play, which is a message coming from PC1 that is just an acknowledgement. Now, this is awesome, because at this point now, PC2 also knows two-way communication is possible. How? Well, PC1 knew that two-way communication was possible when he sent out the send message and got a sync act from PC2. PC2 knows that he has two-way communication. How? Because he sent out a sent act message and got an acknowledgement back. That's how. So now both these PCs know that we have two-way communication. Once the three-way handshake is done, now we can begin our real transmission. Which means if I was trying to send data of just ABC from PC 1 to 2, I just want to say, hey, let's make it a little bit more personal. I want to tell PC2, hello. I want to say, hey man, how you doing? Well, before I send this message, PC1 needs to make sure we have guaranteed information. because I want to make sure that this hello message is guaranteed. I want to make sure PC2 gets this hello message. So before I send hello message, this process begins. We send out our send, then we get our send act coming back to us. This tells PC, well, I know when I sent the message, I got to send act back from that person that I was sending it to, so two-way communication is possible. PC2 starts to guarantee his two-way communication once he sends out the send act message. And then when PC1 gets back an act, that means two-way communication is done. You can look at it in two ways. You can say that PC2 is actually sending him an acknowledgement of the synchronization, or you can say, I'm acknowledging your send, but I'm going to send you a send myself, so please acknowledge it. Because from these two perspectives, PC1 is saying, look, I'm going to send you a send message. Once I get an acknowledgement back from you, I know it's two-way. So PC2 is going to say, I'm going to send you that acknowledgement so you can guarantee your two-way, but I'm also going to send you a send waiting for an act from you so I can also guarantee my two-way communication as possible from my end. You can look at it from that perspective as well. Or you can look at it and say, look, I'm just, I am focusing on the fact that I'm sending you an acknowledgement of your synchronization that you're trying to do with me. Either way, as long as you understand that this must take place, send act, and acknowledgement before this hello even can be sent, that's the key factor there. Now, all this is very important to know because your transformation, and I keep wanting to say transformation, your transmission, and I apologize that I keep doing that, but your transmission is never possible of the actual data that you want to send until this three-way handshake is established. Remember, this is for guaranteed delivery, which means if this was just best effort, this hello would never go through this three-way handshake. It wouldn't even try. Who cares? I'm just going to send it out. But there's no guarantee he's going to get it. So this must be successful. The three-way handshake must be successful before data is sent. If one of these messages never gets back, two-way communication is not possible, either from PC's one perspective or PC's two's perspective. And if that's the case, it's not going to happen. Eventually it'll time out, and PC1 will try to send the information all over again. And this will keep going until the application itself or whatever's trying to establish these flows will time out. If there is no timeout value, guess what will happen? Well, it'll just keep on going forever. Now, Windows has these establishments. This allows me to see all the information that's going on my machine right now. This is a TCP trying to be established. And it's showing you here, from this IP address, which is my PC here, here's this random port number I was telling you about, 53493. That's a random port number. And it's going to this particular IP address with 8080. And it's telling you that we sent a send message, which means we're trying to set up a TCP session with this. Now, there's other messages in here with TCP. You can obviously go out there and look them up. It's pretty cool. It's nice to know what's really going on with TCP. But you also have these established connections. This is telling you that the TCP session has been established. It's telling you that over here it is a TCP session. It's telling you it's been established. Once it has been established, data can flow. Here's UDP. You know, it's just UDP traffic. It's just telling me, look, I just got UDP. Was that going to my address? I was just being sourced from my address. So here, you can also see some of the ports that we're listening on. Here's a port I'm listening on right now. TCP port. It's good to know what your PC is listening on. You might have ports that you really don't want open. This will allow information to come in. You might want to do a research on every port that you have that you're listening on to find out what they are. You might find out that these are viruses. You might find out that it's malware. You might find out this is a port that someone is open. You don't really need it open, and so you go out and you close it. Now, just because it's open and listening on this PC doesn't mean that you can't block it. You can always go in your router and block it. You can also find the commands to make sure that this PC is no longer listening on those ports as well. But once you start getting into this game, make sure that you're aware of what you're doing. You might shut down something that you actually need. So let's talk about these random port numbers. Imagine me going out to a web server. No matter what type of communication I'm going to do, remember guys, we have to build out layer 2, layer 3 information. But since we're trying to communicate with a particular port, since we're using web service, we're also going to have layer 4 information. So, when I'm trying to communicate with a web server, I'm going to send my data. But I'll take this data and I'm going to encapsulate it with what? Layer 4. That layer 4 information is going to have my source port, my destination port. Such as web, that destination port is going to be 80, or 8080, or 443. Now my source port is going to be a random number, just like you saw in my netstack command, showing you all the ports and all the ports that we're listening on, and all the TCP sessions we have established, and so on and so on. That source port is just a random number. 58,212. Now, next time he goes out to send something, when I say he, I'm talking about Windows. The next time Windows goes to send out something, he's going to use 58,2013. He's going to use whatever the next available port number is. That's why we call them random numbers. And that information goes out, because obviously we're going to have the layer 3 with the source and destination IP. And then we're going to have the layer 2 with the source and destination MAC. And this information is going to go out over to the web server. The web server is going to look at the destination MAC and say, oh, well, that's my MAC address. I'm going to go ahead and remove that and take a look at the IP information. Oh, that destination IP, that's for me. And look at the layer 4. Oh, that's port 80. Well, that goes to my web service. Now, just because we have one server sitting here does not mean that it's not doing several types of services. So when this server gets that information and see that it's coming on a port 80, he's going to send that over to his web service. That belongs to my web service. This traffic, as it's coming over to the web server is going to send it to its service, web service. And now when he goes to build the information back, because eventually he's going to look at this data and say, hey, this is a request for information. Let me send that information. So the information he's going to send is going to be what? The data. He's responding to the request. And this is the response. He's going to send data back, which is going to be the response. He's going to build his layer 4 information. And what's that going to be? The source port's going to be obviously himself, which is 80. And the destination port is going to be the source port that came in on the packet in the first place. 58212. Now this makes sense, because if you're going to send out an envelope to someone, they're going to have the address sitting here, 123 Fake Street, and then someone's going to have their return address up here. And we'll say No Avenue. Now this really makes sense, man, because this is the address that it needs to get sent to. When I received this letter coming to Kyle over here, when I received this letter, I don't have to ask them where to respond. I get a request for information. I'm going to respond to that information, and I'm going to build my envelope of my own. And I'm going to take whatever the source information I saw in the letter and put that as my destination. 567 No Avenue. And then my address goes up here. 123 Fake Street. So this makes sense. The information that he got when the packet came in is going to be the information he's going to use to send the packet back. So now he used a destination port number of 58-12, builds his layer 3, builds his layer 2, and sends the data on. That information comes over to here. PC1 says, well, let me look at the layer 2 information. That belongs to me. Let me open it up. Oh, let me look at the layer 3 destination information. That belongs to me. Let me open that up. And then there's the port number, 5812. Oh, well, I know where 58212 goes to. That was that web page that I had open. So this is awesome because if I have 10 web pages pulled up, you know, just all cascading here and all just sitting here, right? If I had all these web pages up, and this was port number 60 and 70 and 80 and 90, well, anytime something was coming in on port 90, it's going to go to this web browser. It's not going to go to these three. It's going to go to this one. Did you ever wonder why, if you had like 20 web pages up, how it always ended up getting to the same one? Well, now you know. Port numbers. But remember, none of this communication is possible until our TCP three-way handshake is established. And that is really good to know. Because if you can't send data, most likely you got a TCP issue. So check it out. Not, I'm not going to say most of the time, but it's definitely something you need to understand is going in the background. The last thing you want to try to figure out is do all these things and rebooting and so on, and realize that your TCP session is never being established. And that's why you can't get communication. So let's take a look at the TCP header here. The TCP header is pretty interesting. We got the source port, which we know now is random for Windows. In most cases, I mean, it could be a static port number. If you only want to communicate from this particular port number and you source it from that port number, the application can do that. So obviously, it knows to come back to that information, to come back to that particular service. Here's the web server. When it actually got the data coming in on this web server, he used this random source port number he might have gotten, but he used a static source port of his own for 80 when he sent the data back out. So it's not always random. We have a destination port. Obviously, if I'm coming from my Windows and open up a web browser, my source port's going to be random. And my destination port going to a web server is going to be 80. If I was communicating with a TFTP server, it'd be 69. If I was communicating via Telnet, it'd be 23. If I was using SSH, 22. Does that make sense? All depends on where you're going and what you're trying to accomplish. Secret numbers and acknowledgement numbers, we're going to be looking at that later on. And window. So this is interesting because remember, this is not source IP and destination IP. Guys, this is just layer 4 information. So when I have a piece of data here, I'm going to encapsulate this data. Now, what does encapsulation really mean? Let's think about that. Our encapsulation means that here's my data. I'm going to put information in front of it. I'm going to put it in this box. I'm going to put information in front of it. I'm going to put it in this box. Now, because I put it in this box, can I see this data anymore? Nope. It's in the box. I'm going to label this layer 4 information. Now, on top of this, layer 4, I'm going to have layer 3, which means I'm going to encapsulate this box with another box, which means I will not be able to see the layer 4 box because it's inside this box. And now here's my layer 3 information, which means now I'm going to even encapsulate it again with layer 2 information. I won't be able to see this box because it's in the layer 2 information. If I said, and let's look at this, I got my layer 4 information, I got my layer 3 information, and I got my layer 2 information. As a CCNA, and a lot of CCNPs will answer this question in this manner. when I ask the question, okay, when I strip back a layer 3 header, or if I remove a layer 3 header, what will I see? And you know what they all say? Most of them, I will see the layer 2 information. No, you won't. Guys, in order for you to see the layer 3 information, you have already stripped back the layer 2 information. The layer 2 has encapsulated the layer 3. And that's what we mean by encapsulation. We have to understand that this TCP header is just for layer 4, which means in my layer 4 information, I'm going to have the source port, the destination port, the sequence number, the acknowledgement number, the window size, which we're going to be talking here shortly. All this information the data gets encapsulated with all this information. And then all this information gets encapsulated with layer 3. It's 20 bytes in size. Well, what does that mean to us? 20 bytes? Well, remember my scale that I was telling you about bits? Let's do it again. A bit is 1 or 0. 4 bits of the nimble, no need to write that. 1,000 bits is a kilobit, but that's not how far we want to go. How about 8 bits? 8 bits equals 1 byte. So if I have 20 bytes, how many bits do I have? What's 8 times 20? 160 bits. So what do we see when we go look at a UDP header? Man, that is beautiful. Source port, destination port. Almost 3 times less the size of a TCP header. Only 8 bytes. Why would we want to use TCP and UDP communication? Well, we want TCP for guaranteed delivery. When do we not want guaranteed delivery? Well, if we want something fast, speedy, and we're not really worrying about it, what if we're sending out data? What if PC1 is sending out data to PC2 every second? Or how about 4 times a second? Do we need that guaranteed every time? Nah, not at all. Not at all. Now, we could have the application on PC2 saying, look, if I don't get information after 3 seconds, then, I don't know what to do. At that point, you can shut down the application, send a warning message, and say, hey, we don't have any communication. I mean, that would be the wise thing to do on PC's 2 end. Well, both of them, because they might need to be communicating back and forth. But at the same time, if this is just a server, if PC1 is just a server sitting over here, and he's just feeding on information, we can actually mix TCP and UDP. I can actually use a TCP method to establish the connection originally, and just from there, just stop it. At that, we're only sending UDP traffic. That's definitely possible. Because we don't want to guarantee 4 times a second that this traffic went across. Not at all. All we want to do is just send the data out. Fast as possible. What can you think that might want to do that? I mean, stock information, that could be one. Think about you designing a network for a stock exchange, where the data needs to be guaranteed, needs to get there quick, fast, but not necessarily 100% reliable. Why would you want TCP traffic to be 100% reliable? I mean, web browsing, wouldn't you? Would you like to get everything guaranteed onto your web page, or you just like to, get whatever might come? Now, again, guys, what does this really mean? Does it mean the stock exchange data isn't guaranteed? No, I don't know. I'm not on the stock exchange network. I don't work on it. And if it was, some data probably would be and some probably wouldn't. But it all depends on the designer of the application and what these people want to do. You have an option. Your option will be UDP or TCP. Pick an option, whatever you want to happen. I know for a fact if I'm doing banking information, don't you think that I will want to do TCP? I mean, you got to admit, if I swipe my card here at, let's see, Kmart, that information comes over here to a server. And where do you think this is handling the process? Here, you swipe your card, comes over to this server, which is probably sitting at a data center somewhere. But where do you think it's going? It's going to some bank over here. Whoever holds the credit card. So don't you think we'd like to have guaranteed information? I bet you the banks want to, because they want to make sure to get their money. They don't want you. We don't want no claims of spending a bunch of time trying to figure out if this card was charged or not. They want guarantee. So our next topic is windowing. Windowing is an interesting concept. Although this graph might not be 100% accurate, we're not looking for accuracy 100% of the time. We're looking for, can you understand the concept? So I want you to think about windowing as a way of me finding out that perfect speed. So here you go. You got this ledge sitting here. You got your window sitting here. And right now the window's closed. So what you do is you open up the window a little bit. And here we go. Here's the window. All right, and you got all these dots on the screen. And air rushes through. Now, eventually, you're still hot. You open up the window to get a little cool. So what do? Let's open the window a little bit more. This allows more air to come through the screen or come through the window and be able to give you cool, and maybe you cool off. Now, what happens if you get a little bit too hot? You get to close this window and lower the flow of air. And that's the concept of windowing. Let's see how this works. I'm going to send one piece of data. And I'm going to send this data from this PC over to this PC. Now remember, windowing is in our TCP. So remember, this is going to be happening via our TCP communication, not our UDP. And I'm going to send this piece of data over. Nice. Now, if I sent this data like this, just like this, the whole time, this might take me 1 week to transfer that data. Now, I get an acknowledgement back stating that I got the data because this is TCP. And then I'm going to send this data again, but I'm going to send it this much data. Ooh, that's nice. I sent this much data. It comes through. Now, at this speed, it might take me 5 hours to download. I get an acknowledgement back, and then I'm going to try to send this much data. Now, at this speed, it might take me 15 minutes to download this file. I get an acknowledgement from this one, we're good to go. Now I get this, I send this much data. This might take me 5 minutes to get my data, to transfer the whole information I need to transfer over. But wait a minute, I don't get an acknowledgement back. Now if I'm not getting an acknowledgement back for all these pieces of data, we got problems. That means somehow this PC, PC2, did not get that data. Now it's time to back off. This is us opening our window every time until the window gets so wide open that we start to lose data. When we start to lose data, we close the window. We shorten it. A little bit more, saying, sorry, too much air is coming through. Let's shut it down just a little bit. And then we get this steady stream of 10 minutes. Have you ever seen data doing this as soon as you download something? 1 week might be an exaggeration, but he might come out and say, this is going to take 7 hours. Then it drops down to 3 hours. Then it drops down to 1.5 hours. Then it drops down to 50 minutes, 25 minutes, and 17 minutes. And then eventually we get this, then we might even drop down to 3 minutes and then probably come back up to our average of 10 minutes. And then it will stay here at 10 minutes throughout the rest of the duration. And this happens quickly. Haven't you noticed this before? This is windowing doing this job. TCP is hungry, which means if you have problems with your bandwidth getting eaten up, and your solution is, let's double our bandwidth. And then you double your bandwidth, and then you say, man, that's getting used up too. Well, let's double it up again. Well, if you're using TCP applications with this windowing will keep going until it can't go anymore. And because of that, you have a potential of eating up no matter what bandwidth you put on there. And maybe quality of service is a better method. We send data out. The acknowledgement that we're getting back is obviously the acknowledgements packets, or not the acknowledgements that we're getting back from TCP, not the three-way handshake, which we're going to talk about here in a minute. Because you saw in the TCP header, we have the three-way handshake, and then we have the TCP header that we were looking at. And in that TCP header, what did we see? We saw secret numbers and acknowledgement numbers. This has nothing to do with the three-way handshake. The three-way handshake has the SYN and the SYN ACT and the ACT. These are messages. So the SYN message is a synchronization message, and the ACT message is an acknowledgement message. These are acknowledgement numbers and sequence numbers. Two different things. Let's talk about our sequence numbers. Sequence numbers is an interesting concept because secret numbers guarantee each data, each packet that's being sent out from PC1 going to PC2. It has this method of understanding how the data, this method of guarantee that the data is coming from PC1 to PC2 by using this method that we call sequence numbers. And let's find out why. PC1 sends out its first packet. Now this is after the TCP session has been established, and now we're starting to send data. And we're sending it via TCP, which means here's my data and what's going to be on top of that data. Guess what? You guessed it. My TCP header. You guessed it. Which is really layer 4, right? It's my layer 4 information. So in this TCP header, we're going to have secret numbers and acknowledgement numbers. Now I'm going to send out a sequence number of 100. Now here's the interesting thing. When this data comes all the way over here to PC2, PC2 is going to say, I got a piece of data with a sequence of 100. Now, PC2 is going to look at that and say, all right, I'm going to acknowledge your 100 by sending you an acknowledgement of 101. Now, this is weird because you figured it would send back an acknowledgement of 100, but that's not the case. When PC2 sends an acknowledgement of 101, he's saying, hey, this is the next packet, the next sequence number that I myself am expecting to see. That's what that means. It's a little weird, but that's exactly what that means. So now with this acknowledgement, don't pay attention to these sequence numbers on this side at this moment. We're not worrying about that right now. So at that moment, or these acknowledged numbers here, we're only worrying about the sequence numbers on this end and acknowledged numbers on this end. So here, I'm going to send an acknowledgement of 101. Because PC1 gets an acknowledgement of 101, he says, okay, PC2 must have gotten 100 because he's expecting to see 101. So I'm going to go ahead and send that. Now remember, behind here is data. As I'm sending this. They're not just sequence numbers. Guess what? It's data behind there with the sequence number on it. So I'm going to send my next piece of data with a sequence number of 101. That comes over here to PC2. PC2 says, okay, I got a sequence number of 101. I'm going to send you an acknowledgement of 102. Okay. That comes back over to here. PC1 says, oh, I'm getting an acknowledgement of 102, meaning that PC2 must have gotten my data with sequence number 101 because he's expecting now to see acknowledgement 102. So now I'm going to send my next piece of data with a sequence number of 102. That comes over here to PC2. PC2 says, I'm getting a sequence number of 102. I'm going to send an acknowledgement of 103 because that's what I'm expecting to see next. That comes over to here. PC1 says, I'm getting an acknowledgement of 103. That means PC2 has received the sequence number of 102, since I'm getting a sequence number of an acknowledgement of 103. So now I know the next sequence number I'm going to send out, and the next piece of data is going to be 103. Now, the reason why you see the sequence number here and the acknowledgement on both sides, the sequence number here and the acknowledgement on both sides, because remember, we got two-way communication here, yes, but this is PC1 sending out his first piece of data. Here's PC2 sending out his first piece of data. The first piece of data he sent was sequence 2. So let's take a look at this. PC1 is going to send out a sequence number of 100. It's going to come over here to PC2. PC2 is going to acknowledge the fact that he got the sequence number, the data with the sequence number of 101 by sending an acknowledgement of 102. However, PC2 has data to send as well. He's going to send a piece of data with sequence number 200. So now, this data comes over to here. PC1 will get data with a sequence of 200 and an acknowledgement of 101. So what does that mean? That means now PC2 says, okay, I got an acknowledgement of 101 from PC2, which means that he got my data with the sequence number of 100. Therefore, I am going to send my next sequence, my next data with the sequence number of 101. And I'm also going to acknowledge that I got PC's 2 data with sequence number 200 by sending him an acknowledgement of 201. And this is where it gets a little confusing because you're just like, I'm kind of lost here. So when you start looking at this data here, you notice that these reds deal with PC1 and these oranges deal with PC2. And this is how it's sent. So here we have data going this way, acknowledgement coming back, but then you have, data sitting here riding on this. Then you have data going this way. So as you can see, the data, as we're leaving, will be here. And as the data is sitting here, attached to this bad boy, as it's coming back. But this is PC2's data. What's in the orange, and what's in the red is PC1's data. And that's how sequence numbers works, which is pretty cool. And that's how your data is guaranteed. So now let's look at windowing along with the sequence numbers. Interesting. Starts to get a little even bigger, right? Now, one of the things that I did not mention, which I'm going to mention here, is what happens when you get the wrong sequence number back or the wrong acknowledgement back. And that's what we're going to look at right here. So I'm going to send one piece of data. Boom. I'm coming over here with a sequence of 100. I'm going to send back an acknowledgement of 101. Telling PC1 that, hey, PC2 must have gotten the data that I had attached to sequence number 100 because he's sending me an acknowledgement of 101. He's expecting to see 101 next. So I send him the sequence number of 101, which is here. And then I'm also going to send some data with 102 on here. This is windowing doing his job. He's starting to send more data. So PC2 sends an acknowledgement back of what? 103. Well, that makes sense because he got sequence number 1 and 2, 101 and 102. He's expecting to see 103 next. That comes over to here. Now I'm going to send 103, but Windows going to say I'm going to try 4 and 5. Now this is an interesting thing. If he's sending 5, what is PC supposed to be sending back to him? 106. But he's not. He's sending 105. Huh. What does that tell PC 1? If PC 1 sent 105, 104, 103, PC 2 should be saying that I'm going to acknowledge you with a 106. But he doesn't. PC 1 gets something back, an acknowledgement back with 105. That's telling PC 1 that, well, wait a minute, I already sent you 105, which means you're not getting 105, which means we got a communication issue here. So at this point, I'm going to lower my window size, and I'm going to resend 105. And when I resend 105, what am I really sending? The same data I sent with 105. I'm resending that data. And I'm going to put that 105 back on there. Well, I don't know exactly. We'll put the exact same 105 on there. It's been a while since I've gone through this with Wireshark to really see how this data moves across. It might use the same secret number, or it might just continue on with the secret numbers that's next in line and resend that data. Again, this is really meant for you to understand how this is happening. Not to be 100% accurate. These are the labs you need to be doing yourself to find out what's really the truth. So my window sizes are going to shorten, and now I'm going to send 105 and 106. Now notice I'm sending the exact amount of data here, even though on this line, I'm sending the same amount of data on this line that I was on this line, even though we dropped the packet and it didn't get sent over. So really, technically, it wouldn't be just one that we wouldn't be sending. It will be two of them that we would not be sending. Which means I'm going to go back to where I know my numbers were accurate. If I sent 3 at a time and I dropped one, why would I send 3 again? I wouldn't. I'm going to send 2. I'm going to shorten my window size. And this is how it all works together, man. This is how your sequence number, your acknowledgement numbers, and your windowing all work together. And it's a beautiful, beautiful concept. And that's how we get guaranteed delivery. Multiplexing is a concept of nothing major. I like to talk about it just briefly. And we'll read what this says up here. The ability to transport different types of data and use port numbers to let the destination host know where the data goes. That's really the concept of multiplexing. That we can have more than one type of data transferring on the same media. Awesome. Which means on my Ethernet, I can run TFTP, HTTP, SNMP, all on the same wire. And what separates that traffic though? How do I know it's HTTP traffic? How do I know this? Oh, by the port number. And this is the concept of multiplexing. Another powerful thing of port numbers. Because when this server saying data's coming in, and let's say we have these nice little queues. HTTP, all's going to go up to here. We kind of got this flow of data coming in, right? Let's say they got these nice little, all this data coming in. And you have this checkpoint, right? This is something I'm just drawing right now. This is not something that's actually accurate. And you got this checkpoint. And at some point, you got this guard sitting here and say, oh, okay, here comes this piece of data. Let's grab this one. Let's take a look at the port number. Oh, your HTTP traffic? Let's throw you through here. Boom. And it's just kind of like this. I think about Men in Black when you had that alien inside the box that was sorting the mail with all those arms. If you haven't seen that movie, I apologize. But that's pretty much what this is. It's grabbing the data real quick, looking at the port number, throw it down. Throw it down. Throw it down. Throw it down. All done by port numbers. This is what we call multiplexing. Because you're able to send multiple protocols down the same media without having all these different types of media and all these different types of protocols to monitor the protocols. Does that make sense? All you have to do is have services on the clients and the servers to listen in on those ports. So let's talk about port numbers. Port numbers are nice because, like I said, with multiplexing, we can use port numbers as a means of listening and sending traffic out. Remember I talked about port numbers were the doors to get through to things. We can use a firewall to shut those doors, keep them all shut, and only allow the traffic that are coming through. Or we can just go on our PC and say, I'm not allowing this traffic. And you would go in there and shut down those ports. And it would no longer be listening on those ports. It's a powerful tool to use. So now, if PC1 is sitting over here, communicating with PC2, and he sends the data out, here's our data. On top of that data, we're going to have layer 4. We're going to build it as if we were looking at the OSI model. That layer 4 is going to have a source port, we're going to say, of 19. And a destination port of 50. I'm going to build my layer 3 information, which is going to have my source IP, which is the IP address of PC1, and the destination IP. I'm going to have my layer 2 information, which is going to have my source MAC and my destination MAC. Man, it's starting to look like the OSI model, isn't it? And here's layer 1. Right? Not really. Because if we're going up in this direction, layer 1 shouldn't be down there. Because after all this is built out, it gets put on the wire. So layer 1 belongs up here. So here's our data. We got 4, 3, 2, 1. Layer 4, 3, 2, 1. That information gets built and goes out what? The PC. Hits the switch, hits the router, switch, comes back over to PC. Now the PC is going to get the data coming in on layer 1, coming in on layer 1 as electrical signal. And what is he going to see when it's coming in? He's going to see the source MAC and the destination MAC. If that information belongs to him, the destination MAC, if that's his MAC, he's then going to see the source IP because he's going to remove the layer 2 information and look at the destination IP. After that, we come into here, and what are we going to see? The source port and the destination port. And then, here's our data. Now, if we do this way, we have what? Layer 1, layer 2, layer 3, layer 4. Why do I keep repeating this? Because it's important for you to know. It really is. Beyond CCNA, you need to know how this works. But nonetheless, this part right here, this port number, this layer 4 information, man, this is important. And I mean really important to know, because what happens if anywhere down the path this port number is not allowed? I want you to think about that. If I'm sitting here on this router and you have a deny for port 19 or port 50, I want you to think about what's going to happen here. First, we're going to deny port 19. That's the first thing we're going to deny. So this traffic goes through, And guys, it doesn't matter in which direction. Think about it. It doesn't matter if I'm denying it going in this direction, or out this direction, or out this direction. Okay? Because as the traffic's going in this direction, if I am blocking 19 from coming in on this router, which is router 1, guess what? We're pretty much done, right? Because that traffic is going to be blocked. Now you got to ask yourself, well, wait a minute, Kyle. We use layer 3 to build our information. Yeah, you sure do. Yes, you do. But does routers work on layer 4? I thought it only worked on layer 5. Well, I mean, layer 3. That doesn't make any sense to me. Well, let's take a look real quick. Let's go into this router here. And let's find this. Let's actually do an access list. I'm going to create an access list, and I'm going to say extended. Oh, I need to say IP access list. Sorry, IP access list. And now we say extended. I was wondering why it wasn't working. Extended, and we'll just give it a name of Kyle. Doesn't really matter. What I want to see here is the output that I get. And I'm going to say deny TCP. Wow. TCP is actually there. I can deny TCP? Well, let's find out. TCP, and we're not going to do it in a real lab. We're just going to see if the command, what commands we have in there. I'm going to say from the source 1.1.1.1 to, and we'll do the wildcard here. And we'll say equal. What does this mean? Match any packets with a given port number. Port number 50. Look at this. We have another port number we can put in. We can have host names. Or we can have a destination address. So I'm not going to put in another port number. I can put in many port numbers as I want here. I'm just going to go to a destination address. And we'll say 2.2.2.2, destination bits. And I also can say, also, equal to port number. What was the port number we're using? Port number, I'm going to move this out of the way. Oh, there it is, 19 and 50. I had it in the, inside the header information. And we're going to say 219. And we're done. Now look at that command I just created. We're going to highlight this command, and we're going to shut this down. This is the command I put on the router. So that shows you, man, that I can actually look at the layer 4 information of a router if I want to. For some reason, people believe that a router could only look at the layer 3, and that's it. It can't go any deeper. But it shows you right there, I can create an access list. I can create a rule saying I want to deny TCP traffic now. Which means what? What is it going to be looking for? What do you think it's going to be looking for? You're absolutely right. It's going to be looking for the IP header information. Not the IP header, I'm sorry, the TCP header. If it's a UDP header, it's not going to be focusing on that type of traffic. But when it opens up that layer 3 information, looks at that layer 4, and it sees its TCP information, it's going to say, oh, that's TCP. Before I forward it on, let me check and see if it's allowed. Because I'm denying anything that's being sourced from 1.1.1.1 that is equal to port 50 and being sent to 2.2.2.2 and equal to port 19. This is pretty to port 19. This is pretty granular. And that's pretty awesome. So now because of this, if router 1 is blocking this traffic in any direction, we might have a problem. So PC1 sends the traffic out. It's sourced with 19, destined for 50, And I'm denying port 19 at this moment. This command was just to show you that it's possible. And I'm denying port 19. Doesn't matter. If I deny it coming in, when it gets to this point, it'll die. If I drop it from going out, guess what? It'll never leave the router. It'll go into the router, just never leave the router. So once this traffic gets here, 19 is blocked, man. It's not going any farther. And you're going to be looking at PC1 and PC2, and you're just going to be like, I just don't understand. What's going on? Where is it being dropped? You won't be asking where would it be dropped. You would ask yourself, why isn't it working? I'm sorry about that. That's what you're going to be asking yourself. You're going to be looking at PC1, and you're going to be looking at PC2, and you're going to be saying, I don't understand. They're set up correctly. And you're going to keep rebooting, making changes, not understanding what's going on. And the bottom line is, it's blocked here. That's why your traffic's not going through. And you're still not going to understand it because you're going to be like, this doesn't make any sense. I ping PC2 from here over to here, and it works fine. It works great. Of course your pings work. But remember, once something pings, everything works. Everything is right. Everything should be working. The number one thing you're going to get as a network engineer, they're going to say, well, Kyle, you're wrong. It's pinging just fine. There's nothing wrong. Oh, really? You're telling me if I have two devices it's pinging, there's nothing else that can be going wrong? That shows me it's getting past the firewall. No, it doesn't. Because what port numbers are you trying to use when you're sending a ping? All that's telling me is the ICMP packets are allowed through the firewall. Doesn't tell me that your traffic... Doesn't tell me that because the ping went through that your traffic's going to go through. So you got to be careful with this. So this layer, this information is very important. This source and destination port number, because every device downstream or upstream you need to realize needs to be open, or else along the path your traffic will get blocked, and your routers can look at layer 4. Remember in the beginning I said you probably, it's layer 2 and 3 is where you're going to be spending most of your time, and sometimes layer 4. That's true, but it's more than you think. It's not just, once in a while I'll deal with transport layer. No, you need to understand how these layers are built. Very crucial. Now, even if this is not the case, let's say I don't have anything blocked, 19 or 50. There's no point of doing 50, because if I show you how 19 is being blocked, 50 is going to do the same thing. Even though I said I was going to show you both. But this information finally gets all the way across here, and it comes into PC2. However, PC2 is not accepting the information. Why? Because PC2 is not listening on port 50. Guys, I want you to understand this. How many times you order a pizza and then you realize, like an hour's gone by, where the hell's my pizza? You call them up and they were like, sir, we were there. No, you won't. I was upstairs the whole time. No one knocked. Yep, sorry, sir, we were there. Now, did he really show up, or did they happen to knock when you went up to the bathroom and you just didn't hear the door? How can you open up a door if you're not listening to it, if you can't hear it? How can you open up a door when data comes to your door if you don't listen out for it? You can't. How can you answer a telephone ring if you don't hear it? You can't. Okay? So these ports this PC needs to be listening on port 50 in order to receive that information in on port 50. So port numbers are really important to understand in that fashion. You can have port numbers be transmitted with TCP or UDP. You would have the server, let's say this is a server, you would have the server listening on the ports for the services you want to provide. If this is a DNS server, you need to have port 53 open. Otherwise, it's not going to do its job. No one's going to be able to communicate with it. Our source port numbers are obviously the port numbers that come from the person who is sending the data. Because when that information comes over here, let's recap and let's go through this again. Get rid of all this. PC2 is getting this data with this information coming in. When he goes to send the information back over, because this data here is PC asking for a request. This data is going to be him sending back the information that was requested for him. However, when he goes to build his layer 4 information, he's going to be using the information that came from where? PC1. Since it was sourced by 19, obviously he's going to put the destination as 19. And the source is going to be himself, which is going to be source 50. The IP header, what's that going to be? The source IP address is going to be source IP, destination IP. The source IP obviously is going to be PC2, and the source IP is actually going to be PC1. How does he know to send it back to PC1? Because PC1 put it in this information to begin with. He put the source IP address as himself. So when PC2 gets that information over here, he knows that it was sourced from PC1. So obviously when he goes to send the data back, he's going to put PC1's IP address in the destination IP because he wants to get it back to PC1. So these source and port destinations, these source and destination IP addresses and MAC addresses, crucial. Now we have a certain thing called well-known port numbers. They're the first 1,024 port numbers. And how many port numbers do we have available? And I'm going to click here. And let's see what our first 1,024 numbers are. You even see right in here, Wiki, it says well-known port numbers. The first 1,024. That's a lot of port numbers. Notice that we stop at 1,023. And let's go take a look at some of these port numbers. Notice that our port number list says TCP, UDP. If it's blank, it means that it can't be used as TCP in theory, based on the fact that at this moment, this is the way it is. Status means that it's official. That means this is the way it is by the powers that be. You should know that the first 1,024 are well-known port numbers. So some well-known things that you need to understand. Well-known port numbers that you really should know at the top of your head by the time you take your CCNA exam. And pretty much throughout your networking career, you're going to forget, man. It's just very simple. There's times that I've forgotten 23 for Telnet. I'm like, is that 22? I mean, even SSH. I kept calling it SSH 25. I don't know why. It was just something that I did. So FTP, SSH, TFTP, SMTP, DNS, Telnet, HTTP, HTTPS, POP3, DHCP. These are ones that I will commit to memory. I tried to do the TCP and UDP aspect of it. Man, I failed every time. I just took it out. I was just like, forget it. I'm having a hard enough time remembering the port numbers. I'm not going to try to remember if it does TCP and UDP. And that's pretty much with port numbers, man. That's pretty much how they work and how they function. So this whole lesson was really about TCP. The three-way handshake, sequence numbers, and port numbers. And don't forget acknowledgments as well. And remember, we have synchronization and acknowledgments in our three-way handshake, but we also have sequence numbers and acknowledgement numbers in our TCP header. Unfortunately, when you're learning these courses, normally you get confused with those, and usually the instructor is not separating those two. And that's really the bad aspect of it, because you need to understand that three-way handshake is just to guarantee that two-way communication is available. And then the TCP session or the TCP headers will allow that guaranteed delivery to take place. And our data will not go any further until that TCP session has been established. If we're using TCP as a mechanism, as a mechanism of transmitting our data. It's the best way to say it. Okay? So now, communication types. In our layer 3 header, we're going to have a source IP and a destination IP, which you saw me write as SIP and DIP. So our source IP, let's say this is PC, this PC over here, 192.168.1.1, and this one is 200.1.1.1. If the data is originating here at PC1, trying to get over here to PC2, when he's building this layer 3 information, which PC1 is going to be building this information, he's going to have the source IP of 192.168.1.1 because that's his address. So it is being sourced from him. The destination IP address would need to go to 200.1.1.1. So when that traffic leaves here or come over to the router will look at the layer 3 information and say, oh, the destination that you need to go to is 200.1.1.1. That, in order for me to get to 201.1.1.1, I need to send the information out this interface. Hits the switch, come over here to PC2. Now, when PC2 looks at that information and looks at the layer 3 information, remember he's going to look at the layer 2 first, but he looked at the layer 2, he opens it up, and the layer 3 information has a destination of 200.1.1.1. Now, he's going to look at that and say, well, that's my IP address, so this belongs to me. When PC2 send data back to PC1, and let's ask the question why. Why would we want to do that? Well, I sent out a request. So this information here to 200.1.1.1.1, I'm requesting information from PC2. PC2 wants to reply to that information. So his layer 3 information is going to be, the source IP is going to be himself, and the destination IP is the information that he received originally from the source. PC1 sent me data. I know it came from PC1 because his IP address is in the source. So when I need to reply to this information for PC1, I'm going to look in the source information in order to find out who sent it to me. So when I know I need to communicate back with him, that's the IP address that I'm going to go to. So therefore, as that's the IP address I need to go to, that's going to be my destination IP address. Just like I was talking about with the letter and the envelopes when you're mailing. But because we have a source and a destination, we're going to one destination. That's it, guys. That's it. It's plain and simple where we're going. We're coming from here and we're going to here. Period. We call this unicast because we have one source and one destination. We're communicating between you and another person. We like to call it unicast because it's only one person. Uni means one. Because from my perspective, I'm only talking to one person. From PC2's perspective, I'm only talking to one person. Hence the concept or the term unicast. We're sending it one-to-one. Broadcast. Now, broadcast is the concept of sending one message to all. In my layer 3 information, this is PC1, 192.168.1.1. He is going to have a source IP of 192.168.1.1, and he's going to have a destination IP of all 255s. Now, when you get to learn subnetting, you'll learn that there's another number we can use, but this concept, in this concept that we're learning here, all 255s, which means you're saying right here, I am 192.168.1.1, and I'm talking to everyone. Whenever a switch gets a broadcast message, which this is a layer 3 message, not layer 2. If it was a layer 2 broadcast, it would be all Fs. Kind of makes sense, doesn't it? Since we kind of learned a little bit about hexadecimal and how we have 0 through 9 and A through F. And because we learned that, that's kind of the last digit in each one of the numbers, right? In each one of our sets of numbers, the highest number could be is 255. So if we send something to all 255s in every number, it's a broadcast. If each one of our digits are at 15, or in our scenario here, or in hexadecimal meaning F, then what does that mean? We're sending it out as broadcast. Now, the reason why I only drew these PCs is because a router, by default, does not forward broadcast messages. It does not. So whenever a router gets a broadcast message, because he will get this message, it stops right there. The router doesn't forward this traffic. There's ways of dealing with that, but at this moment in your CCNA studies, just know that a router does not forward broadcast messages. So that broadcast will get all the way up to this interface, and this will die. Right then and there. So a broadcast message is one to all. So now we can talk about multicast. Multicast is interesting because here we got this PC, and the layer 3 information will be source IP, will be 192.168.1.1, and the destination IP will be a multicast address. Now, multicast addresses start with 224, and you'll learn about that later on. So let's say we have a multicast address of 224. Let's say we have a multicast address of 224.1.1.1. I'm going to send it out to this address, and this is saying that, look, I am the source right here, and I'm communicating to this address. Now, really what this means is I will be communicating to anyone who is listening on this particular address. And that's interesting because multicast is the way of having PCs listen on an address. So if this PC, if all these PCs are circled and they're listening on 224.1.1.1, that means when 192.168.1.1 sends traffic to the 224, the only ones who are going to get that traffic are the ones who are listening. Now, a switch will still send it out of all ports. It treats a multicast as it does a broadcast. A switch will treat a multicast just like it would a broadcast. So these switches will get it, but they'll drop the information because they're not listening. So that's really nice to be able to have traffic coming from one source and going to many. And that's the concept of multicast. So you'll be using a special type of address to do this type of communication, but it's one to many. So unicast is one to one, broadcast is one to all, and multicast is one to many. Now, anycast is a little weird because imagine having this cloud here. And you got your router 1. And you got your PC sitting over here somewhere. And you go out and you want to find a web server. And let's call it Yahoo. And we got these 3 Yahoo servers scattered across the world. The interesting thing about this is I'm going to give each one of these servers an IP address. Now, you would think that I would give them different IP addresses, but this is the one time that I can actually have the same IP address. And with any cast, let's say it's 200.1.1.1, this one's going to be 200.1.1.1, and so is this one. The concept with Anycast is this message goes out, and then whoever gets this information first will respond back to that PC. Now, based on what I understand about Unicast, is these bad boys will have communication with each other somehow, and, you know, it'll stop them from, you know, once they realize one is responding to it, you know, this one here, we'll say server one. Server one might get the information and say, okay, I'm going to respond to this, guys, and let server 2 and 3 know that, guys, I got it. Don't worry about it. But you're not going to be dealing with Unicast. You're going to be dealing with, you're not going to be dealing with Anycast. You're going to be dealing with Unicast, broadcast messages. Multicast, you will deal with in some aspect, but you won't be learning multicast in that fashion as far as building a multicast network. And these are our communication types. So when I say Unicast in the future, you should know what Unicast is. If you don't know, you need to go back and review to find out what it is. Unicast, this term right here, uni means one. Multi, this means going to many. And broad means you're hitting everyone. Now, let's talk about basic communication. Remember in the very beginning when I told you that a PC needs two things to communicate. It needs an IP address and a MAC address, which means without these two things, a PC using TCP/IP cannot communicate. It cannot happen. Now, since the main thing we need always with communication is IP address and MAC address, because of that, every PC builds the information that's going down. Now, you saw as I was building this information, when PC 1 has to send this information out to PC 2, he's going to have our data. Now, we're talking about basic communication, so we're not going to have layer 4 information in there. But we are going to have the source IP and the destination IP. Now, the source IP obviously is going to be me, and the destination IP is going to be the IP address that we're trying to communicate with. So since I'm getting the destination IP address from PC 1, because that's the PC I'm communicating with, so if I'm sending a ping, and I say ping 192.168.1.2, well, obviously, me typing this in is going to force the PC or tell the PC, this is your destination IP that we're trying to communicate with. So that will go here. .1.1, right? Or 1.2. That's where it would go. And the source would be me. Now, the source MAC and the destination MAC, that's something a little trickier. Because the source MAC, I know what my source MAC is because it's my network card. All I got to do is look at my network card and get the source MAC. No big deal. But the destination MAC is a little different. How do I fill in this field? I must have a way of being able to fill in this field. And the only way to do this is to have a list of MAC addresses on my local PC that corresponds to the IP addresses. Now, this is important to know because I need some type of table to say, look, the MAC address, if this was the MAC address of BB, :BB, I would say, look, the MAC address of BB equals 192.168.1.2. If I had this type of information on this PC, a PC 1, then when I go to build my source MAC, which is easy to do, and my destination MAC, which is not so easy to do, all I would have to do is look in this table and say, oh, I have an entry here for 192.168.1.2, and that MAC is BB. And this is how my destination MAC is built if I had this table. Now, wouldn't that be wonderful if a table like that existed? And it does. And it is called ARP. Address Resolution Protocol. And what ARP does is it builds a table for each local PC. Every local PC has every PC has an ARP table, and it builds its table by matching IP addresses to MAC addresses. Now, when this happens, it has to get the information from somewhere, shape, or form. This table isn't magical. So let's find out what happens. PC1 tries to communicate. Now he starts going down and he starts building his information. First, takes his data. Then he takes his layer 3. Source IP, destination IP. Then he goes and he builds the source MAC. And then he tries to do the destination MAC, and he's like, okay, so what do? I need to look in my what? My ARP table. Guess what? I don't have an entry for my ARP table. Now, that's kind of interesting, because what am I looking for? I'm really looking for the MAC address, my destination MAC. I'm looking for the MAC address of my what? Destination IP address. If the destination IP address is 192.168.1.2, what's the MAC address? I'm going to look in my ARP table. And I'm looking for the 192.168.1.2 address in my ARP table so I can find the MAC address of that IP address. But guess what? It's not there. If it's not there, what do I need to do now? Well, I'm going to have to send out what is called an ARP request. And in that ARP request, I'm going to have the source IP of 192.168.1.1. I'm going to have the destination IP of 255.255.255.255. Wait a minute, what did we just learn about that? That's a broadcast address. I'm going to be sending out a broadcast. Well, what else do I need? What do you always need for communication, no matter what you're doing? IP address and MAC address. So even with this ARP request, I have to fill out these headers. Wow. Yes, everything that goes out, it needs to go through that stack. So I'm going to have a source MAC, and we'll say that source MAC is AA:AA, which would be this PC here. Easy enough, look at my own network card. And I'm going to have a destination MAC, because I don't know what it is, of all Fs. Now this packet, or this frame, goes out and hits this switch. What does a switch do with a broadcast? It sends it out every port except the port that it came in on. And you're going to hear me say that a lot more times. A switch will send the broadcast, all broadcast messages, out every port except the one it came in on. So that broadcast hits this, goes out all these ports, including this one. That traffic gets over to here. He's going to look at the destination MAC, the layer 2 information, and says, oh, it's a broadcast. Well, I'm going to open it. It's a broadcast. Well, if that's a broadcast address, I'm going to open it, man, because broadcast goes to everyone. So I'm going to open up the information. I'm going to say, oh, it's an ARP request. Okay, well, let me respond to that ARP request. This might be incorrect. You might want to go back into your Wireshark and pay attention to this aspect of it, because this might be broadcast as far as layer 2, because we don't know the MAC address, But since we have the destination IP address originally when we did our ping, this most likely will be the IP address of 192.168.192. Nonetheless, I want you to think about the logic here. Whether I'm 100% accurate that this is a broadcast or not, it's either going to be a broadcast or a unicast. Whether it's a broadcast or a unicast, guess what? PC2 is still going to get it. Well, let me reply back to that. So he's going to have his data, and he's going to respond by filling out the layer 3 information, source IP and destination IP. Let's do that. Source IP, it's going to be 192.168.1.2. That's my address. Destination IP, 192.168.1.1. Where do you get this information from? How does he know that the destination needs to go to 1.1? Because when PC1 originally sent out the information, the 1.1 address was in his source field. So PC2 is smart enough to look in the source field when that data comes in and says, oh, this is a ARP request. Well, I'm going to take that source information, and since it was sourced from 1.1, I'm going to send it back to 1.1 with the information that 1.1 was requesting. All from the layer 3 header. Layer 2 looked at the layer 3 header, saw that it was sourced from 1.1, so he's going to destine that information back to 1.1. Now here, this is when it gets interesting, because now he's going to source, his source MAC is going to be his address, which is BB, and the destination MAC, which he already had in the layer 2 information, AA. So now PC2 has all his fields filled in. He sends that information back over to PC1. And when PC1 gets it, he's going to see all this information. And when he sees all this information, he's going to say, oh, it was sourced from BBBB. So the source IP address, which I was trying to communicate, the destination IP address of 1.2, this information is now being sourced from 1.2, which is the original PC I was trying to communicate with anyway. And the source MAC address of 1.2 is BBBB, which means that is his MAC address. So now I get to fill in my ARP table, BB:BB. Now that is done. Now I have the ability to communicate with PC2 directly. And from here on out, I'm going to be filling out my destination IP, 192.168.1.2, and now my MAC address is going to be BB. And where did I get this information? Bam. I got it from ARP. Man, that's just crazy. Are you telling me that everyone has an ARP table? Yeah. It's a poor guy in my class who, the poor guy was for some odd strange reason believed that, PCs don't have ARP tables. And I'm like, yeah, they do. All PCs have ARP tables. So let me show you. And I did this command, and I'm like, there's your ARP table. And the poor guy never came back to my class again. I don't know why. Guys, it's very common to make mistakes. It's very common. I can guarantee you I just made a mistake right now on this video about that being a broadcast layer 3 address. I can almost guarantee that it's a unicast. Guys, do I care? No. Is it embarrassing? Of course it's embarrassing when you can't remember anything. That's part of us being human. Yeah, it's embarrassing. We want to know it all and be right all the time. But guess what? We're not. Because we are human, we do get embarrassed, and because we are human, we do forget. Learn to get past that just by screwing up 1,000 times. When you screw up 1,000 times, you get so used to it, your 1,001 time doesn't really matter. I screw up all the time. Just don't let it affect you to the point that you don't want to learn anymore. That's the ultimate key. Now, as I look at this information here, you can see that every IP address that I need to communicate with has a MAC address in my ARP table. This is fantastic. It shows you that whether it's static or dynamic. And normally, obviously, when I'm doing a dynamic means that I actually use ARP requests to get this information dynamically. I had to send out an ARP request to get this. And this is very crucial to understand. Because at some point, if your ARP table becomes corrupted in any way, shape, or form, you're going to be sending data to the wrong MAC address. And transmissions or communication will not happen. It's possible to have this done, and the problem is we don't really think about this communication on a regular basis. We learn about it, we go through our CCNA, we understand it, and then eventually we just forget about ARP because it all kind of works itself. But if ARP does not get the information in its table correctly, because once the information is there, it's there. Unless the information gets timed out or refreshed in some way, shape, or form, that information is there. So you might have to go in there and physically clear out entries in your ARP table so it will send out another ARP request to fill that information in. You can actually do manual entries, which will make them static. And then when you do that, I mean, you could be typing in the wrong MAC address, you could be sending data to the wrong PC. And it's definitely possible. And you could have communication coming back and forth. It might be hitting the wrong PC, though. It's possible. Now, based on this, after we've got our ARP done, and we're able to communicate now back and forth from PC 1 and 2, let's go back and re-look at this process all over again. PC 1 tries to communicate with PC 2. Step 1. I'm going to send a ping. Step 2, I'm going to build my layer 3 information, which has my source IP and my destination IP. That's easy to find. My source is going to be this, the destination is going to be who I'm pinging. 3, I'm going to build my source MAC, which is easy. This is my layer 2 information, and my destination MAC, which is not so easy. I need to use ARP to get this destination MAC address. Now, when I use ARP, I have to go back and look in where? The ARP table. If the information isn't in ARP, then I have to do what? An ARP request. Once that ARP request is done, I can continue on by building my source and destination MAC. So technically this comes up and goes here. 7, I can send this off to communication. So let's try this with the MAC address that's already in there. Here's my ARP entry. ARP BB:BB equals 192.168.1.2. PC tries to ping 192.168.1.2. The first thing he's going to do, he has data that he needs to send. He's going to build his layer 3 information, which is what? Source IP, which is 192.168.1.1. The destination IP, which is 192.168.1.2. And now I'm going to encapsulate this with layer 2. My source MAC obviously is going to be AA:AA, which is me. That's who I am. And my destination MAC. At this point, I'm going to look into my ARP table. At what part am I looking for? Where am I going in the table? What I'm going to look for? I'm going to be looking for the destination IP address, which is this. 192.168.1.2. When I see that in the ARP table, then I'm going to go over and say, oh, okay, This is BB colon BB. And this is how this is done. Let's talk about the default gateway, because there's other things that play a factor in basic communication. When PC1, or in this case PC8, tries to communicate with PC1, we need to understand one thing about this, and PC1 is going to send the communication over to PC8. PC1's in network A. PC8 is in network B. Now remember, I explained that the IP address numbers that we have identifies what network we're on. We have the network number, we have the host number. So PC1, if he's trying to communicate with someone on the same network, like on PC3, he's going to go through the steps that I said. He's going to build the layer 3, he's going to build the layer 2, and in order to get the destination MAC of the layer 2 portion, he's going to look in the ARP table. He's going to do this if they're on the same network. But wait a minute, what if they're not on the same network? Aha! If he's not on the same network, he's not even going to try to look for ARP in that fashion. He's going to send it to what? His default gateway. Now, what is a default gateway? A simple explanation of a default gateway is this. A default gateway means that anytime you're sending data or you need to communicate with someone that's not inside your network and who's not on the same network as you, you need to send it to that default gateway. Now, we have to think about the logic here, because what device is going to be the default gateway? That's an interesting question. We have to ask ourselves, well, wait a minute, if PC1 is trying to communicate on someone on a different network, what device do we need? What layer do we need to use? And what type of device do we need to use that communicates between networks? A router. And a router deals with layer 3. Right? So that means my default gateway must be most likely a layer 3 device. Does that mean I can send it to a layer 2 device? Sure. Doesn't mean the traffic's going to get where it needs to go. Now, that means if everyone here is on the 192.168.1.0 network, which means this is a network, this is a network, this is a network, this is host. Remember we talked about that? That means this interface of this router needs to be on the 192.168.1 network. So let's give it a 192.168.1.10 address. So PC1 is going to have an IP address, 192.168.1.1. And he's also going to have a default gateway of 192.168.1.10. So whenever he needs to communicate with someone else that's outside of his network, he's going to send it to this address. So now let's take a look at this communication. So in this interface, which is router 1, 192.168.1.10. Isn't that much better? PC1 is trying to communicate with PC8. PC1 has an IP address of 192.168.1.1 and a default gateway of 192.168.1.10. Now, let's think about how this communication goes. He's trying to communicate with 192.200.200.8. We'll just make that the address. So this is the interesting thing, because here's how PC1's information is going to be. His source IP and his layer 3 information is going to be 192.168.1.1. That's simple. His destination IP address is going to be what? Well, PC1 knows the destination that he's trying to communicate with. He knows that this is not on his network. So guess where he's going to send it to? His default gateway. What is his default gateway? 192.168.1.10. Well, that makes sense, doesn't it? When we're building out layer 3 information. This is where it gets kind of weird, because you're like, well, wait a minute. That doesn't really make sense to me. Because if I'm sending it to 192.168.1.10, how does it know that it's getting to 192.168.200.200? How does it know that? Well, that is an interesting question. An interesting question indeed. Because our original header is definitely going to have this address in there. So how does this information get to 200.200.8 and keeps this information in there, but yet I'm sending it to my default gateway? This is where Wireshark comes into play. This is where you want to actually look at your traffic and see, if I'm sending traffic to my default gateway, how is this happening? I'm a little confused on how we're sending it to here in order to let the router know that it needs to go in this direction. And this is where Wireshark will come into a huge play. Alright, so I decided to do a different approach on this lab here. Instead of kind of going back and forth to this, this is what we have. This is what we were talking about. This is where we were in our program or our lesson. And I was kind of drawing this out with PC8 and so on and so on, and having all this. This is going to be kind of just kind of a mess. So I'm going to go ahead and close this out. And I'm going to bring up a different document here that I have created. And the question is, where is it? There it is. Okay, so as you can see here, it's going to be the same. It's going to be the same layout as far as our diagram we were looking at, or our lesson that we were looking at, which is right here. So PC1, 2 is going to be over here, obviously, in Network A, and PCB is going to be over here, and PC8 is going to be over here in Network B, and of course we're going to have a router here. One of these interfaces is going to be in this network, one's going to be in this network. And we're going to kind of bring this a little bit farther up here by stretching this out. And we're going to zoom that in. And we'll just go ahead and shorten that up a little bit. So that's really how this is set up. We have PC1 and PC2 sitting right here on the same network, and PC8 is sitting over here, and in between here we have a router. Now, as you can see, we have this interface in 192.168.1.10, which obviously the network number of 192.168.1 is identical to these two PCs, which means they're on the same network. And here's PC8. Now, I've given them specific MAC addresses so we could see this traffic as we're looking at it being sniffed. We're going to look at this traffic as a Wireshark. And we're going to be able to see this traffic. So there was no point in me actually putting the MAC addresses on here. It's because they're pretty straightforward. All right, now you can see up here, if it's not too small for you to see, it says PC1, here's PC2, and over here is PC8. So first we're going to verify that our IP addresses are correct and what our MAC addresses are. So pretty simple, 192.168.1.1. That's for PC1. You can see down here that we are labeled PC1. And look at our interesting MAC address. All ones, saying that, hey, we're PC1. So let's take a look at this one. (192.168.1.2), as you can see it over here. And look at our MAC address, all twos. Very easy, okay? Now let's go over here to PC8. And as you can see, 192.168.2.8 and all 8s. Take a look at our ARP table here. So you can see I don't have anything for the other PCs yet. So let's take a look at our traffic. And as you can see, we already got a bunch of stuff going out. So let's go ahead and change these options here. And I want to say host 192.168.1.2. I just want to look at that traffic going to 1.2. So we don't have to weed through all that traffic. Now I'm going to look at this ping command, because I only want to do a count of 1. So let's go ahead and let's shrink this just a little bit. And let's ping 192.168.1.2. And who am I again? I am 1.1. So I'm coming from this PC over to here. I'm going to do a -n for count and say 1. So I did 1 ping. Now here's the information. Let's see if we can make this a little bit bigger here. So the information is a little bit bigger so you guys can see it. So it makes it a little bit less manageable, so to speak. So let's kind of stretch this out a little bit. You can see they're kind of bleeding in together. And we're going to discuss exactly what we're looking at here in each one of these columns. I should be able to split this. Let me figure this out here. Alright, well, I guess the length and the info are just going to have to be merged together, I guess. Alright, so starting from left to right, we got a number. Now, this number pretty much tells us the packets as if they're going out. And obviously, I can change this by clicking this. And obviously, number 1 goes to the bottom, and number 16 goes to the top. I stopped the capture because we're going to start getting a bunch of Microsoft traffic and stuff like that. We don't want to see that. So I'm going to go back to the very first data that we captured that went out. Then we have time. Now, time, obviously, is pretty much going to match up if this time is doing it one by one. Obviously, it's going to catch. Don't worry about the time. Source. Now, this is important because this is saying where is the data being sourced from. Now, I can change this and notice that my numbers are now not in 100% order, which is nice. Okay? So now we know we can always go back to our original order of data that's leaving. So that's nice. So a source tells us who we source from, and we can put them in order, which is nice. Obviously, we can get all the ones that are sourced from here, all the ones that are sourced from this address, so on and so on. So now we also have destination. And that's good to know as well. So we can sort by all these, and another one is protocol, and then the length. Now the length, for some reason, I can't separate the length in the info in Wireshark. I even tried it on my PC, and I just couldn't do it. I don't know why it's attached like that. But nonetheless, we have the length of the data that's going out. How long is it? And, or the size, how big it is. And then we have this info. And some of this is helpful, and some of it's not, but most of the time, it's going to be pretty helpful for you. So we're going to go back and do this number by, we're going to do it by the numbers, which means we're going to do it as the first data that we captured went out when I did that ping. Now, let's take a look at this red marking here. Let's full size this. And this red marking is a TCP, and that's not what we're concerned with. We're concerned with that ping. Now, remember, the first thing I talked about was ARP, right? as the traffic is going out. And when did we discuss this? We were talking about basic communication, and we were talking about the ARP table. So as we see in our Wireshark here, first thing we want to do is kind of shrink this down somewhat, or just bring this down here. Notice that the first message that went out when I tried to ping was a broadcast address. It was sourced by what MAC address? By me. I'm on PC1. It was sourced by me, and it was destined as a broadcast. Now, if we look at this information, this is nice that it gives us this information by telling us exactly what the source IP and the destination IP is. However, we really need to look at this data here, because this is what's going on. Now, notice that this is an ARP message. It says Address Resolution Protocol. Now, if we go up here and look at this first line that we're actually seeing, which is actually really number 2, but 192.168.1.2. This is the description now. This is the info. It says, who is 192.168.1.2? Notice it's a broadcast, and the protocol that we're using here is ARP. So here is our ARP information. Remember that encapsulation information that I told you about? Well, here we are. We're encapsulating this data with Ethernet information, which means that the real data here is the ARP request. This is the message that I'm trying to send out. This is the data that I'm trying to get to someone. I don't know who it is specifically, so I sent out a broadcast. So I'm going to encapsulate this data by putting this Ethernet information on top of it. What is this? Well, this is our source MAC address, and here's our destination MAC address. Well, doesn't that look familiar? What's a source address, a source MAC address, and a destination MAC address? What is that? That's right, our layer 2 information. So when that information goes out, it's going out with this first. No one's going to see the ARP information until they open up and remove the layer 2 information. And this is why we call it encapsulation. So the data will be at the bottom, and then we'll have all these layers on top of it. Well, this is the layer 2 layer. Now, this is the frame. This is the entire frame that goes out. And what we do here is we take all the layer information, and we're going to bundle it into this Ethernet frame. And here we go. Here's the frame. And this frame has a lot of information of all the stuff that's below us. And there you go. However, this is where we stop here, which is layer 2. As you can see, the source MAC address is myself, all ones. And the destination MAC is all Fs, meaning it's a broadcast. Now, this is really nice to know, because as he sends this information out, the first thing he's trying to do is, I'm trying to communicate with PC, with the actual address of 192.168.1.2. This is wrong. I'm going to change this in a minute. 192.168.1.2. I'm trying to communicate with this. So the first thing I'm going to do is I'm going to look in my ARP table. Well, guess what? It's not there. Because remember, I must have the source IP and the destination IP for communication. I must have them both. So I use the ARP table to give me the MAC address for all the IP addresses that I'm trying to communicate with. What's going to happen now is, if I don't have it in my ARP table, what am I going to do? I'm going to send out a ARP request saying, who is 192.168.1.2? I'm going to send it with a destination of all Fs, which for layer 2, that's a broadcast address. That comes into here. This switch says, oh, okay, I understand that. It's a broadcast. Let me send it out all switch ports, except the one I came in on. All the switch ports. So router 1's going to get it. he's going to open it up and say, well, you're asking about 192.168.1.2. So that's not me. I'm not worrying about it. This PC is going to open it up and says, oh, you're trying to find out who 192.168.1.2 is? Well, that's me. And then I'm going to send information back. I'm going to reply to your request. So let's find out the next information that happens with our Wireshark. So the next piece of information that happens after this one is done, notice that I get information that is sourced from PC2. How do we know this? Because it's source 2.2.222222. Remember, guys, anytime you're getting data that's being sourced or destined by the MAC address, that means we're just doing layer 2 communication, right? A lot of people don't know this. A lot of people get kind of confused when they start seeing this, like, what's going on? Why are these, what are these numbers? They're MAC addresses. And it's just layer 2 communication. So look at the information that's coming from 2.2.2. I'm sorry, coming from 192.168.1.2, coming from MAC address 2222. And it's coming back to me. And it's still an ARP message. Or ARP protocol, I should say. So let's go take a look at this. Notice that every time I click here, it changes my data below. So right now I'm on the second message. So let's take a look at this ARP. Notice this is an ARP reply. The original one was an ARP request. Now this one is an ARP reply. He's replying back. Now if we go back to this one, to the request, look what it's saying. Here's what's in the ARP request. This person who sent it was 1.1.1.1. Now, isn't that nice to know who sent it? It is. Because now, when I need to go reply to this, I know who sent it, so now I can make sure that I send it back to 1111. I have the sender's IP address in there. That's nice to know as well. So I can send it back to the IP address and the MAC address. Because what will happen when he tries to send this information back and he doesn't have the IP address of the person who originally sent it, or the MAC address of the person who originally sent it? He would have to do an ARP request. And if this information was never sent back and forth in this fashion, we would just constantly be sending ARP requests back and forth. So this also allows me, PC2, whoever I'm sending it to, which, remember, we're sitting on PC1 now. We sent this information. We're looking at the request now. This allows whoever I'm sending this information to build their ARP table as well. Because when PC2 gets this information, he's going to say, well, I mean, while I'm at it, I might as well just put this entry in my ARP table. Might as well. Target MAC address, target IP address. And notice the zeros because we have no idea what those values are. So when a reply comes back, which this is now the reply we're looking at, let's see what he says. Sender MAC address is 2. Sender IP is 1.2. Now that's nice to know, because now when this comes back to PC1, PC1 will now update its ARP table. That's the information it needs right there. Now remember, the original packet or original frame that we sent out, it was a broadcast message. And let's look at the layer 2 information. Our destination from PC's perspective was a broadcast. But now when that perspective was a broadcast. But now when that information comes back, guess what it's going to be? The destination is going to be specific. So a broadcast goes out does not have to be a broadcast when it comes back. It's a layer 2 unicast message now. Once this is done, PC1 can now build his ARP table when he gets this information back, and now he can send his ping. There it is. It's a ping request. What is a ping request? A ping request is just saying, please reply back to me. If we look at this information, let's find out really what's in a ping message. It specifically says this is an echo ping request. It is requesting for you to send something back to me. And just send the data that I'm sending to you, send it back to me. That's what the echo is. So let's look at this. There's our data. All right, that's really what we're sending over there. And look at our data down here. A, B, C, D, E, F, G. It's just the alphabet. N, O, P, Q, R, S, T, U, V, W, and then it starts with A, B, C again. And this nice little thing here that says, hi. How you doing? And that's what's in a ping when we're sending a ping from PC1 and from Windows. So now we're going to get the message, a reply back from a ping. Let's see what it says. Same thing. Because we asked them, look, send back an echo reply, please. A request. I'm requesting you to reply back to me. So the original one was a request, and the information that comes back into PC is the reply he was expecting to see. And that's it. We got some other ARP stuff here, and starting to get into some Microsoft stuff, so we don't really care about that. But this is how the information begins. So whenever you're configuring something, if the first couple of pings fail, what do you think is happening? We're probably trying to resolve ARP. We probably sent out an ARP message. And if we sent out an ARP message, we have to wait for it to come back. And during that time, as we're waiting for it to come back, you know, we've already failed that ping. Now I'm going to go ahead and fix this diagram here. Now, let's go back and take a look a little bit deeper here with this ping. As I send out my ping requests, here's my data. We looked at the data that's going out. Guys, you can get really granular with this as far as going to each one of these fields. I'm just using this as a means of showing you how this is done. But this is a very awesome tool to use to be able to really see the data that's coming out of your network interfaces and going through your network. So this is really our data here, and we encapsulated this data with an ICMP message. Now, what does that mean? An ICMP message. Notice that when I'm looking at the ICMP message, I can't see the data. I have to open up this in order to see the data. I had no idea data was there until I opened it up. And oh, there's a data. Let me open this up and see really what the data is. Okay? This is the concept of encapsulation. Inside the ICMP message, there's data that's been encapsulated. On top of this is the layer 3 information. Here's our source IP and our destination IP. So whenever a router gets this information, he's not going to see the ICMP packet. He's just going to see what? This. He has to open this up and remove this in order to see that it is an ICMP packet or ICMP message. So this internet protocol, which is version 4, this is just IP information. You can actually see all the information that's in what we discussed, the IP header. This is the IP header. You got your version, you got your header, and down here you have your you got your flags, and the most important aspect of it is our source and destination. Here's our source IP, 192.168.1.1. Remember, we're still sitting on PC1, and our destination is 192.168.1.2. This information is encapsulated with layer 2 information. And look at our source information and our destination information coming from PC1 to PC2. Isn't it nice to have the MAC addresses set that way so you know which PCs they are? And this is the real reason why looking at Wireshark to make you understand this concept of encapsulation. And we take all this information and we bundle it into a frame and send it on its way. So we got a pretty decent look at what this looks like, this whole concept of basic communication. We have our data, which in this concept is really just an ICMP message. In that message, there is some data, but really here the data is the ICMP message. And we encapsulate that with our layer 3 information, which the routers will use to make forwarding decisions. And on top of that, we encapsulate with layer 2 information, which is what the switches use to move data. So when that information comes into this switch, he's going to look at the layer 2 information. The first thing he's going to notice, let's take a look at this layer 2 information. Oh, the source MAC address. That's 1111. Do I have that in my MAC address table? Nope. Let me go ahead and add it. And I'm going to add it onto this interface, which will be FA01. And then 02 will be PC2. Then it's going to say, well, I need to send it out to 2222. Do I have that in my MAC address table? If not, what am I going to do? Send out a broadcast. This is the switch now. If I do have it in my MAC address table, oh, I see that now. Which port is it attached to? It's attached to port FA02. Let me just switch that data that came into here right out this port. This is why this information is very crucial for basic communication for you to understand. Very important. So, we're going to find out now what happens when the PC communicates with someone on another network. So originally we were saying that when I need to communicate with this device here, I'm going to have a source IP, and this is from PC1's perspective. I'm going to have a source IP of 192.168.1.1. I'm going to have a destination IP of 192.168.200.8. I'm going to have a source MAC of 11 and a destination MAC of what? Now, the question was, because a lot of people ask me this, well, wait a minute. The PC1 knows that he's communicating with someone outside of his network. So if he knows he's communicating with someone outside of his network, he needs to send it to his default gateway. So if he needs to send it to his default gateway, that means my source IP needs to equal 192.168.1.1, and my destination IP needs to equal 192.168.1.10, because I'm sending it to my default gateway. Ah, well, that's interesting. That was the original question. That's how this lab started all in the first place, right? A lot of people think this way, and I want you to understand the logic. That whatever's in my destination field, on my IP header, and I'm going to be using an IP header to forward data, whatever is in that field means that that's the destination that I need to send the traffic to, which means it goes no farther. So if I put this destination IP address as my default gateway, I'm saying that my default gateway, which is router 1, is the destination of this packet. It doesn't need to go any farther. It needs to go to router 1. But that's not where the packet needs to go to, is it? The packet needs to come over to here. So when router 1 gets it, he knows if it's this information, he knows that that's from him, and he's going to open it up. He's not going to forward it on if the traffic is meant for him. There's no point. Routers make their decisions, their forwarding decisions, based on the layer 3 information. Well, if that's the case, then my destination, in order for it to get here, must be 200.8. Otherwise, if I change that destination over to here, it'll never go past this IP address. And that's exactly right. Then how do I send it to my default gateway? How's that even possible? Well, let's take a look at it. First thing I want to take a look at is my MAC addresses here. Let's see, show IP interface brief. Because we don't have the MAC addresses written up here, so we want to see what they are. Show run, or show interface, FA00. So for FA00, look what I put the MAC address. Well, that was pretty nice of me, wasn't it? It's just all zeros, and the last digits is 168, meaning that we're on the 168 side. So let's take a look at FA01. Well, that's nice. We're on the 200 side. So obviously, if I pull a MAC address of the 200, I'm on this side. If I pull a MAC address of the 100, I'm on this side. So let's go take a look at PC1. And let's see how PC1 handles this traffic. We do want this running in the background. We're going to hide this ink here. And we want to change our options. We want to go to 200.200.8. This is the host we want to pay attention to. Let's go ahead and start our traffic. I'm going to still do a in count of 1. I want to say 200.200.8. Notice we got nothing. Let's try it again. And this is just a count of 1. Nothing. First of all, let's make sure I got my options here correct. Yep. So let's take the in out. Let's try to see if we can get any traffic coming back. So now I can troubleshoot and figure out what's going on. First thing I want to pay attention to, can I hit my default gateway? What is my default gateway? Ping 192.168.1.1. Nope, 1.10. And I can't even hit my default gateway. So let's find out why. This might be a VM issue. Okay, I found the issue. It's not going to accept PC1 as far as the router is concerned. The router is not going to accept this as a ARP entry because of the fact that I set it all to ones. And this has to deal with multicast. So I'm not going to get into that explanation. The bottom line is PC 1 and 2 will be able to communicate with those MAC addresses, but the router will not bring that 1.1.1.1 in the ARP table. All right, so let's just go into PC 2. And let's see how this traffic works. It does say PC 3, but that's fine. Let's bring up Wireshark. I just forgot to change the name of the account. And let's go to interface. Let's go to options. And we want to look at the 10.200.200 host. 10.200.200.8. That's the host we want to focus on. Let's move you over. And we're going to ping 192.200.200.8 and 1. Now, let's see the first bit of data that goes out. We got our ARP and we got our reply. Now, let's really take a look. Let's bring our ink back here on what we had. Let's move this over. And let's look at what information we really sent. Now, remember, PC2 we're going from a source of 192. Let me change these preferences here. All right, notice our first thing here. Notice our first communication is 192.168.1.2. That's where we're going from, and we're going to 192.200.200.8. So what does that mean? We're going to an IP address that's on a different network. So now, let's take a look at how that traffic's getting there. Here is my data, my ICMP message. Let's take a look at this. Well, wouldn't this make sense that 192.200.200.8 will be the destination? Because remember what I said, the destination is where the traffic ends. And that's it. If that's where it ends, that's where it ends. So because of this, how do we get it to our default gateway then? How? Well, let's take a look at the layer 2 information. Very interesting. Remember that 168 address? Isn't that this one right here? There it is, 168. Oh, so we're moving the traffic to the default gateway by the MAC address. Very interesting. So this brings me to my next point. How does traffic move from one end to the other? Because remember, the most important part of this is every time we send data out, what are we building? We're building our layer 3 information, which is our source IP and our destination IP. We have our layer 2 information, which is our source MAC and our destination MAC. Very important to understand. Now, the information that's in here is crucial from end to end. Now, when I say end to end, I mean if I'm trying to communicate with PC1 over to PC8, this is going to be really important information to know. And how we, and when I mean know, which means every time we go from device to device, you need to know what's in the layer 3 information, what's in the layer 2 information. So I'm coming from PC1 over to PC2. What's PC1 going to do? PC1 is going to try to ping 192.168.1.2. Now here's our fields that we have. Our layer 3, we have our source IP and our destination IP. For our layer 2, we have our source MAC and our destination MAC. Because we're trying to ping 192.168.1.2, this is an easy field to fill up. Because that's the destination that our ping request is going to go to. The source IP information is pretty easy as well, because that's us. So 192.168.1.1. Now let's look at the layer 2 information. Where are we going to get the layer 2 information from? The source MAC is pretty simple, 1111. The destination MAC is something that's a little difficult to get. Where do we get the destination MAC address when we're trying to communicate with other PCs? We get it from the ARP table. And the ARP will have a destination or a MAC address of 2222, which equals 192.168.1.2. If this is not in the ARP table, which actually it's flipped around, but if this is not in the ARP table, we're going to send out an ARP request. That's a broadcast address that gets sent out. The switch will send it out all ports. PC will eventually get it and bring the traffic back, which we saw. If it's in here, there's our answer right there. That's where the destination MAC address goes. Pretty easy communication. Now, let's build this when we're trying to communicate with someone outside our network. Our source IP is easy. But we're trying to communicate with PC1 and PC8. The destination IP address is 192.200.200.8. Our source MAC address is going to be us as well. And of course, for us to look at this, we need a destination. So we're going to look in our ARP table. Now, here's the interesting thing, though. TCP/IP knows that this is not on our network. And if it's not on our network, we cannot communicate with it. So where do we send this traffic? To our default gateway. Okay, now this is pretty interesting to understand. If it's our default gateway, what is our default gateway? Our default gateway is 192.168.1.0. I'm sorry, 1.10. That's where we're going to send the traffic to. So now our destination MAC address will be the MAC address of this default gateway. And I'm going to look in my ARP table for 192.168.1.10. I'm going to look for the MAC address. If the MAC address for my default gateway isn't in my ARP table, what am I going to do? I'm going to send out an ARP request for this. It's going to come back and say 00 colon, what was it? 168. So actually it is 01 colon 68. There's our 168 right there. And my destination MAC address will be what we change, not the IP address. There is a difference between traveling layer 2 and traveling layer 3. This is a concept that most have a hard time understanding when we talk about layer 2 and layer 3. So now, I'm going to leave the layer 3 information the way it is because I have my data sitting here. I have my layer 3 header, which is going to have the source of 1.1 and the destination of 200.8. I'm going to encapsulate this with a source of 11 colon and destination of 01 colon 68. See, at layer 2, it's not looking at the fact that I mean, layer 2, it literally is not looking at the fact that, wait a minute, this is not the MAC address for 208. It doesn't look at it like that at all. We're just focusing on the layer 2 destination. Layer 2, which are the switches, forward information based on the destination MAC. Now, I can create an ARP entry on here on my PCs and say, hey, for this particular network range, send it to this particular MAC address. And that will be sitting on this particular router. You can make traffic go anywhere you want as long as you understand how it functions. If you get anything out of your CCNA, I want you to understand this really, really well. How this data moves. When that data, because we have a source, we got a source IP of 1.1, destination IP of 200.8. We got a source MAC of 1111. We got a destination MAC of 0168, which is this interface right here. Now, when that traffic comes up to here, and that switch, when it gets that information, knows that that MAC address is sitting here, he will forward on to router 1. Router 1 will look at that layer 2 information and says, oh, that's for me, let me open it up. And what does the router care about? Layer 3. So he knows that data goes to him, he's going to look it up, and guess what he's going to do? He's going to forward it based on a destination MAC address. And it'll come down here, and you're good to go. So let's take a look at our PC's MAC address. I have to bring this VM up here again. Now, let's take a look at the ARP request for not PC1. This should be PC2. Let's find out the IP address. This is 1.2. I don't know why this is PC1. I changed the host name on it. That's fine. But anyway, you can see up here we're on PC2. This is saying PC1. It shouldn't be. Let's we can easily avoid that annoyance right there. And let's say ARP-A. Let's take a look at this ARP. Now, what is 1.100? Let's find out. ipconfig all we're going to try to ping the 200 address and see what happens. Because in our ARP table, we have 1.10, which is my default gateway. Here's the MAC address, and there you can see it, the 168. This is something else. Don't have to worry about that right now. At it. Let's try that. Still nothing. There we go. Okay. So notice that the first one failed, and that's because of our failed pings. 10 address is my address in the house, so I always want to type in 10, so I apologize. Our first one failed because we had to send out an ARP request. So let's now take a look at our ARP. Notice that we don't have an ARP entry. Huh. Why? I don't understand. I pinged this address. Well, the reason why this is we don't have an ARP table for our entire network. Our entire... Okay, so when I say entire network, I mean, let's look at it like this. So because of this, PC1 will have ARP entries for everyone that's on his network. If it's someone that he can communicate that's locally to him, he's going to have the MAC addresses of every one of those PCs. Because they're on the same network. But if I have a router sitting here, and its address is 1.1.1.5, and he's my default gateway, I am going to say all traffic that doesn't belong to me, send it to 1.1.1.5 with MAC address 5555. And that's it. That's all I care about. So the broad range of your ARP table is how many PCs is on that network. And when you are communicating with anyone outside your network, you're going to be going to the default gateway. And since you're going to the default gateway, I don't need to know what the ARP information is for that. Because when I send this to my router or to my default gateway, I know for a fact, or I'm under the impression, I don't know for a fact, but I'm under the impression that I'm going to be hitting a layer 3 device. And my ARP information is for me to communicate via layer 2. Well, this makes a lot of sense now. So with layer 2 traffic, that means I need to be using MAC addresses. And if I am communicating between PC 1 and 2, I'm really communicating via layer 2. Why am I communicating via layer 2 if I'm using IP addresses? And this is the biggest confusion that plays a factor. You're using layer 2 traffic because the switch will forward that traffic via your source and destination MAC addresses. It'll build this table with the source MAC addresses, but it will forward them based on the destination MAC addresses. And that alone is why we say it's a layer 2 network. The layer 3 traffic will never be forwarded with the layer 3 information, the layer 3 header information, until we get to a layer 3 device. So we need MAC addresses. If we're working on a switch and working via layer 2, we need MAC addresses. We need the destination MAC. If I need to communicate with an IP address outside my network, well, guess what? Here is my layer 3. This is where my layer 3 network begins. This is all layer 2. So if this is all layer 2, and notice I drew in this interface. If all this is layer 2, that means all I care about as far as the MAC addresses is what is in my layer 2 network. That's what I need to have in my ARP table. There's no reason to have the 10.200 or the 192.200.200 address because I'm sending it to him anyway, and I'm not going to be communicating via the MAC address anymore or layer 2. I'm going to be communicating via layer 3 because I'm going to transit a layer 3 device. Now, when that traffic comes back into this router, obviously that traffic is going to turn from layer 3 back into layer 2. Because the router is going to say, all right, I need to send this to 1.1.1.1. That's on the same network as I'm on. I'm going out that same interface. Let me look in my ARP table. Oh, wait a minute. You're telling me a router has an ARP table as well? Let's go find out. Router 1 is what we're using. Show IP interface brief. Show IP ARP. Well, look at that. 1.2. Now, 1.1 is not going to be here, remember, because we set his MAC address to all ones, and the router's not going to take that because of multicast. Now, in the layer 2 address, because of multicast, there's certain bits that can't be turned on if it's not a multicast address, and that's what's happening here. Now, because of this, look at PC2 and look at his MAC address. Here is his own interface. Wow, he even puts that in the MAC address table, right? And it even tells you what interface we need to go out of. So when we look at the routing table and say, okay, traffic's coming in on this router, I needed to go to 192.168.1.1. He's going to look at the routing, the interface, and see that it goes out of interface 00. He knows he needs to send it out this interface. He knows it needs to go to 1.2. I know I said 1.1, but he knows it needs to go to 1.2. He's going to look in this ARP table and build the source MAC address of himself, which is 168, and the destination MAC address of here. We are consistently communicating either via layer 2 or via layer 3. And that is the crucial aspect of this lesson. So, now let's get back to our drawing here. So at any given moment, you need to be able to know what is in our IP header. This is crucial. If I ask you these questions, this is one of those questions that I can almost say for sure you probably would get on your exam. I don't know, I haven't taken the new exams yet, but I can honestly tell you that this is something that you need to be doing and understanding. Not just for the exam's sake, but you should know this. And it's a lot of working parts, so it's very easy to forget. You just have to keep going back and remember. So now, PC1 is going to communicate with PC8. Let's see how we're going to build this. PC1. We're going to have a source IP of 192.168. Let's do it this way here. We're going to have a source IP of 192.168.1.1. We're going to have a destination IP of 192.200.200.8. We're going to have a source MAC of 1111. We're going to have a destination MAC of what? The default gateway. Why are we going to do the default gateway? Because this is not on our same network. So the destination MAC is going to be 0168. Very important to understand. Knowing this power, you can send traffic anywhere you want just by changing the destination MAC address. And that switch will forward that data based on it. So now this traffic, what does it do? Goes through the switch. The switch looks at it and says, oh, you have a destination MAC address of 0168. That sits on this. I'm going to bring you over to here. This router gets it, opens it up, the layer 2 information, says that's for me, removes it, looks at the layer 3 information, and says, oh, okay, well, that goes out this interface. So now he has to rebuild this information. Rebuild it, yes. When information comes into the router, we don't just forward it on. We have to rebuild the source destination IP and source and MAC. So what's the source IP going to be? Remember what happens when you have a source IP coming over to PC2 or PC8. PC8 is going to change that information to its own. And I said that correctly, just not 100% clear. So here I have a source IP. This is 192.168.1.1. This is 192.200.200.8. Source IP 1.1, destination IP 200.8. So far, so good? Don't worry about the source of MAC. We're talking about layer 3 now. So when that traffic comes over here, PC is going to say, Okay, this traffic was sourced by 192.168.1.1, and it was destined for 192.200.200.8. Now, PC2 is going to say, all right, I understand this. Now, whenever I need to send traffic back for this particular, when I need to send traffic back to 192.168.1.1, what am I going to do? I'm going to put that as my destination IP. And now the source is going to be me. Very important to understand, especially when I'm doing a ping request. I'm going to send the ping this way, saying, hey, I'm expecting an active reply. Because it was sourced by 192.168.1.1, he knows that that information needs to be destined for 192.168.1.1. And his source IP will be himself. And he will send that traffic back over here. So if I have a router here and I say, okay, well, we're sourcing it from 192.200.200.10, then my destination over here will be what? 192.200.200.10. Well, that doesn't make any sense, because then it's going to go to the router, and then the router is going to say, oh, that belongs to me. Let me open it up, and it goes no farther. So how do you get back here? Well, apparently the router has to make sure that the source information remains the same when he is rebuilding this information. There's no reason for him to change the source IP. And what about the destination IP? Remember, if we change that, it'll never get to his destination. So that must be the same as well. Now, what about the source MAC? Well, that's a funny thing, because remember I told you that, as I showed you with those IPs, that those MAC, those ARP tables are only for the local network? Haha. Well, that means something, because if it's for the local network only, 192.168.1.10 is not on the same network as 192.200.200.10. So how are we going to do this? Because PC8 will never have this MAC address in here, but he can have this one. So we're going to change the source MAC address to my own, which will be 192.200.200.10. And of course, the destination MAC is going to be going to this PC. So that means the source IP and the destination IP never changes, which makes sense, because this is layer 3 information that we need to get from point A to point B. And if we make any changes to this whatsoever in our transit path from point A to point B, and of course this will be my transit path. My transit path will be going to here, to here, to here. This all in transit. Think of a transit path as all the things that you do or pass as you're going down the street. Now, if I had to come through here, and this was a decision point of where to go, you see my point? And let's call this Apple Cider Street. We'll say it's on a different road. Somewhere it changed. Doesn't really matter, but this is a decision that we have to make. We got several places to go. We can go in this direction, or we can go in this direction. So we have to make a decision. And at this point, this is a decision maker. So I'm going to decide to go straight from this point. And I'm going to go straight. Here's another decision maker. Okay? And I'm going to decide to go straight. And here's another decision maker. I'm going to have to go straight. So, guys, these are routers. Every time you're driving, you're making routing decisions. And you didn't even know it. You're making these decisions. You are the router every time you come to this point. Here's router 1. Here's router 2. Here's router 3. And every one of these are your transit path. Every time you're sitting at a traffic light, every time you need to turn, every time you need to make an exit, you are transiting it a router. That's exactly what you're doing. So this is your transit path. So when someone says, what's your transit path? Oh, I had to go through, and what do we call these? Intersections. I had to go through Apple, Elm Avenue. I had to transit through Apple, Tree Street, and I had to transit through Apple, Plum Street. And there's your transit path. So when you're going through your transit path, if you change the source and destination of those IP addresses, well, you're gonna find your traffic not going where it belongs. So why do this? You wouldn't. So the router makes the decision of saying that I'm going to change the source MAC address, though, and the destination MAC address information. This will make sense because on this side, we'll never know anything about on this side. Very important to understand. Let's take a look at what our layer 2 information is and where we're forwarding at layer 3. Here's our layer 2, layer 2, layer 2, and right here is when we're making a forwarded decision via layer 3. Okay? So let's take a look at it like this again. Router 1, here's PC 1. Here's PC 1. Here's router 1. Here's router 2. Here's router 3. Here's router 4. And here's router 5. And here is PC 2. 192.168.1.1, 192.200.200.8. PC 1 trying to communicate 192.168.1.2. He's going to have a source IP of 1.1, a destination IP of 200.200 or 200.8. Now, because this should never change, we should know no matter where we see this data, before it gets to PC2, it should have the same source and same destination, no matter where we see it. But because this is layer 2 information, this is layer 2 information. What about between here? These two routers. Layer 2, layer 2, layer 2, layer 2. These might be IP addresses that we're sitting on, and we might be making 40 decisions of going out but these two still have MAC addresses. And if they still have MAC addresses, they're going to be sending that traffic via what? Think about that. We're going to have the source as it's leaving this interface. We're going to have the source IP and the destination IP. But the source and destination IP is for what traffic? We're forwarding somebody else's traffic. This source and destination is for this traffic. The only way we can move the traffic is via the source MAC and destination MAC. Which means we, going from router to router, we are using the layer 3 information that we never change to make our forwarding decision, but we are moving it via layer 2, going into this interface and coming over to here. I know it sounds kind of weird, but remember, these informations here, the source and destination MAC addresses, they're going to change every time. So I'm going to have a source and MAC address of 11 to 168. Is that what we had? 168 going to here. Then I'm going to change that for my source MAC address. Maybe it's 169 and send it over here to 170. Because that's the MAC address of here, 170. Then I need to forward that. I'm going to change the source MAC address to 180. And make the destination to 181. That's why it goes out here. Now this is a point-to-point link, which we'll discuss later on. If that's point-to-point, then that makes sense. That it doesn't really matter. It's just, whatever we send out here is this is going to get it anyway. But we still have to have the layer 2 information, because how does the PC know it's actually for him on the router? So every time we go through here, every time, we're going to have a different source MAC and destination MAC. This will be one source MAC and destination MAC. This will be different. This will be different. This will be different. So let's go through this again. One more time. This will be a particular source and MAC address. Source and destination. That information will change when it's leaving this router. When it's coming into this router, it will be whatever it left this router. Then, as we're sending it out the source and MAC address will change. And this keeps happening, which means no matter where I'm at, I'm going to have a different MAC address coming from here to here, source and destination MAC address, than it is going from here to here. Very important to know. So this basic communication seem to become somewhat complicated. So we know all these MAC addresses now. So as I'm building this, I'm going to have a source IP of 1.1, destination IP of 200.8. I'm going to have a source MAC of 1111, destination MAC of default gateway, right? Because it's outside of my network. And that's going to be 0168. Now, when router 1 goes and resends that information out, he is going to have a source IP address of 1.1, a destination IP address of 200.8, the source MAC of 1111. Really? No. Remember, it was sourced from PC1 in this perspective, coming in this interface. But when I need to leave out this interface, 1111 is not on this segment. So now I have to replace this source MAC address with my MAC address of this interface because it's on the same network as this one. So now the source MAC address is going to be 0200, because there's our 200. That's what we made it, right? And our destination MAC will be 8888. So if I would have asked you, as the packet is leaving router 1, tell me what the source MAC address and the destination MAC address and the source IP and the destination IP would be, you would have this information. This is all you would have. This is all you would have. And I would write your question and say, packets leaving this interface. What's the source and destination MAC? And I'll just give you a bunch of IP addresses. I mean, a bunch of answers, which will have the source and destination IP and the source and destination MAC. And you, off the top of your head, should be able to do this within a minute. In less than a minute. You know why? Because you know the source, the MAC addresses will always change. And you know the source IP addresses never will. I mean, the source and destination IP addresses never will. And the source and destination MACs will always change hop by hop. The second that I'm going to be leaving my network, those MAC addresses, source and destination, are going to change. And that is pretty much it with our explanation of basic communication. It's very crucial to understand this because basic communication is how all our PCs, routers, and switches communicate. Remember, we might be learning routers and switches, but what's connected to those routers and switches? PCs. So we want to know how that traffic comes from the PC, comes into our router, how the router communicates with the host, and sends that traffic on. And this is pretty much our basic understanding of communication. So, network types. Network types is kind of a broad type subject. It can mean many things. But in our world, what we're going to discuss is some different terminologies that we would use on a regular basis. The first one we're going to start off with is PAN. Now, what this means, now there's a lot of acronyms in CCNA. I mean, a lot. And you're going to find that even in your CCNP and CCIE, there's a lot of acronyms as well. But when you're getting into your CCNA training, it's so many that you have to learn that it can become cumbersome. So what is a PAN? The P stands for personal. And the A and N stands for area network. So the word area means really the area that you would normally have this in. So if we have a personal area network, that really means that it's personal. It's between you and you. I mean, that's really what it means. It's your network. Now, this can mean a lot of things, but the idea of what we want to emphasize here is that the personal means something that's very close to you. So a personal will be you and your cell phone. Bluetooth. Bluetooth is a technology that is personal. You hook up your earpiece, you use Bluetooth to communicate with that earpiece, and it only has a very short range. We have earphones that can be used as Bluetooth as well. You can hook it up to your computer, and you can walk around your house with Bluetooth earphones. But again, there's only so far it can go. Now, PAN is not something you're going to see often. And in fact, you probably never hear it again in our course. LAN. LAN stands for local area network. Now, this is a big one because local area network is technically how you define it. Now, what do I mean by define? Anytime I use the word define, it means definition. How do I provide a definition for local? If you are defining this word, it can mean anything. Seriously. I mean, here we would consider traditionally a local area network is a network in the same building. Some consider a local area network being on the same subnet, being on the same network. Some feel that local area network is anything that we can get to within a walking distance. Which means you see that you have this connection here with this router and this WAN connection going across, this serial connection. What if we didn't have this? What if this was just a router that was plugged in right across the street or right next door? You know, we would have to come out the building and walk across the street and go into this building. Some people consider this still local, both these buildings. They're local to us. So this is identifying where our locations are. Local just means is local to us. Now, ideally, local also means, it can mean several things to other people as well. Local, some people define local as using Ethernet. It's local to us, so we're using Ethernet connectivity. So anytime you say, well, you know, we need to do some work on the LAN, everyone just automatically thinks, okay, we're dealing with switches and we're dealing with nodes, and that's it. That means no routers are involved. So this could mean to someone that the local area network is something where it's all layer 2 communication. So because of that, this definition of local area network is pretty much kind of a wide range. It can mean several things. Ideally, think of local area network as really the definition of something being local to you. It doesn't mean that others who have this type of different definitions of the local area network, that you can't adapt to those. When someone says local area network, you might have a different definition of it. You've defined the word local in a different way as someone else has defined local. But nonetheless, you know the word exists. And because of that, you should be able to ask someone, well, when you say local, are you talking about just layer 2 traffic? Or are you talking about the entire building? You know, a question like that. I mean, that's a really legitimate question. All depends on how someone defines it. WAN. Now, this is pretty self-explanatory. Wide area network. This means we have a connection that's across a wide area. Now, think of these two IPs connected somewhere down the line. And this was not here. And this was in Texas. And this was in Maryland. Well, you do have this connection going to the internet, coming across, and you have a peer connection between these two sites. Maybe that's not the case. Maybe you don't have these links at all. And maybe you just have this leased line or this long cable that's going from one side to the other. And this will be your WAN, your wide area network connection. Or maybe you do have it just like this. You have a connection between your two routers, and you have your connections to the internet. And I can communicate from Texas to Maryland between this link right here or through the internet. But the second that we are going outside our building, outside our local area network, when we're leaving our local area network, we are transitioning into the wide area network. Does that make sense? So wide means long range. Hence the term WAN, wide area network. Now, MAN It's pretty much the same as wide, except it's saying that we're not just doing wide connections. We're going from metropolitan to metropolitan areas. Hence the word MAN, Metropolitan Area Network, which means we're connecting two metropolitan areas together via this particular, however we're going to connect them, whether with one link, several links, but we're going from one metropolitan area to another. Now, this concept of the cloud is something that you're going to see a lot because the cloud always emphasizes the internet. That's how we see the cloud. And the word cloud is thrown around all the time. I mean, it's thrown around so often that people who don't know the word cloud just use it as everyday conversation. Well, where did your traffic go? Oh, it went somewhere in the cloud. Well, that's not really a good explanation. However, this is what people do on a regular basis. It's in the cloud somewhere. Who knows? That's where it went. Nobody understands the cloud, right? Well, the concept of the cloud is you do understand the cloud concept. You just don't know what's in the cloud. And that's really what the cloud means. It means that from here, everything that I have in this diagram, I know about. Either I control it, I know it exists, but I know what it is. When my traffic leaves this router 1, and goes in through this interface and hits this cloud from this end, I might know about this end, but anything past this, I have no idea what it is. So this might be your ISP's router. This might be router 2 sitting here. And you don't know how router 2 is configured, but you do know the IP address of this router, and that's it. And in this cloud could be thousands of routers that it would take for you to get to your Texas site over to your Maryland site. So I could draw the cloud like this. Instead of having these two, I could just have one big cloud. Or I could draw it like like I already had it. Two separate clouds. But the cloud means we don't know what's going on in there. So like a VM. Give you a perfect example. The last video I did, I had 3 PCs. PC 1, PC 2, PC 3. To you, each one of these PCs are individual, but that's not what these were. These PCs were nothing more than not even real devices. I mean, they're just what's a good word? I'm trying to think of a good word to explain it. I guess the best way to say is it's a piece of software making you believe you're sitting on hardware. That's the best way to explain it. Because I could say it's a piece of software, but isn't that what Windows is anyway? Because I have Windows 7s on all 3 of these machines. And they all sit on this server here. You're accessing them as if they're 3 separate machines. To you, they look like they're 3 separate machines. So when PC 1 wants to communicate with PC 2, what would it have to do? I mean, technically, when you're sitting on PC 1 and communicating with PC 2, it makes you believe that you're directly connected to those devices. When in reality, this is really what's going on. Somehow behind this communication, we have connectivity, but we don't know what that connectivity is. We might think we know because it makes it makes it look like that. But technically, this is how we draw it. The cloud symbolizes that we don't know. And that's really the big thing with the cloud. Devices that we have on our land. Now remember, our LAN is our local area network, and we can define that land as as a sense of area where it's located. The fact that we're just using layer 2. And based on what I'm going to explain to you now, you might get down to that understanding that, well, this really LAN means layer 2. Because the devices that we have on the LAN all work on layer 2, including this router. And we're going to see how. So our first LAN device is a switch. Now, we know switches are used to connect multiple devices for communication purposes. So if I connect PC1 and PC2 here, they will be able to communicate between each other without any problems. Now, that's nice because if I have a 24-port switch, I can hook up 24 devices, and my network is starting to grow. Now, we also have this router sitting over here, and we all know that this is a layer 3 device, and this switch is a layer 2 device. But we need to understand, as we were looking at our last video, the layer 2 and layer 3 information must be built. And this router here, this interface is a LAN interface. It might be a layer 3 device, but it's connected to our local area network. Now that's a little weird because I could have another router sitting over here and have it connected to my local area network and even have a connection between them. These are still LAN interfaces. It's not until I leave my network in some fashion will that traffic be moved by layer 3. So anytime my traffic is going up to this router, and between here, we're really doing layer 2 communication. Technically, between the two routers will be layer 3, whenever you're communicating between two routers. But remember what I said before. I might be sending traffic from router 2 to router 1. However, I must build the layer 3 information, encapsulate that with layer 2, and the destination MAC address, as is coming from router 2 to router 1, better be the same, which means this destination, this needs to be layer 2 here. So this layer 2 information, this destination MAC, needs to be the MAC address of router 1. If it's not, router 1 is going to drop it. This is where what I was saying earlier might be a little confusing to others when I say we might be using layer 3 to make our forwarding decisions, but we still have to build the layer 2 information. When we're routing between routers, I still need to have the layer 2 information. And that layer 2 information must be the correct one going to router 1, or else router 1 is going to drop it. If this does not happen, I can't send the data. And what you're going to get is an encapsulation error. It'll say encapsulation failed. If my ARP table's messed up, that'll happen as well. I'm sorry, but I don't have anything in ARP. The ARP request isn't working. For whatever reason, it's not working. If I don't have the destination MAC address, I can't finish building my layer 2 information. Therefore, my encapsulation failed. So because of this is all still LAN devices. I have a LAN switch. I have a LAN interface on my router. And I also have WAN connections on my router. And I have this LAN connection between these two, which means even though these are two routers and they're communicating with each other, they're still on my LAN. So you can say that LAN traffic just deals with layer 2, but in this scenario, it's not. It's dealing with layer 3 as well. That's why sometimes you have to ask people questions, ask them to be specific, because in somebody's mind, they're not looking at it that specific. They have it in their mind. This is what layer 2 traffic is. This is what a LAN is, and it's not really 100% clear to them. But they think it is clear to them. Now we also have this interesting thing called a hub. Now this hub is also a device that can sit on our LAN. However, a hub, no matter what is happening, a hub is just a means of connecting PCs. There's no intelligence with the forwarding decision, which means every PC that is sitting on this device will get the traffic of every other PC. Where a switch, that's not what a switch does. A switch will only send the traffic to the ports that it belongs to. Now, based on that, if PC5 sends traffic going in this direction, if PC5 sends traffic going in this direction, PC3 and 4 is going to get it, even if it's meant for PC1. Every time someone communicates on a hub, everyone gets the traffic. So this is a LAN device as well, but it doesn't work on anything. It's really a layer 1 device because we're not making any forwarding decisions. Some people call this a layer 2 device because to them it's a LAN device, therefore it's layer 2. See where that confusion comes into play? Would they be wrong saying it's a layer 2 device? Technically, yes, because a layer 2 device is something that would use the layer 2 information to make forwarding decisions. Or filtering, or, and that filtering would be either allowing or denying the data. But with a hub, I can't do that. I can't make any changes to this hub. All this hub does is allow traffic to come in and go out all the ports. So it's really a layer 1 device. Now, bridges is the concept of having this, let's say I have this bridge sitting here, and he's connected here, and then over here we'll have either another switch or a hub. And this hub here, let's say you have tons of devices. Let's say each one of these are 100 devices. PC 3, 4, 5 are each 100 devices, simulating 100. So that means we have 300 devices sitting here, and we have 400. And let's say everything was slowing down, things were getting really humongous, traffic was slowing down, and let's say we decided that we wanted to add a bridge. Now that's nice because then I could take half that traffic, because let's say we had 600 as well. I mean, PC6, which would be another 100. And we're going to move PC5 over here. So originally PC6 was sitting over here, giving us 400 addresses. I'm going to move PC5 over to here. So what I've done is I have this bridge sitting here. And what I've done is now on this side of the bridge is 200 MAC addresses. 200 PCs. Over here is 200 MAC addresses. Now, a bridge gives me the ability to say, okay, I need to speak to PC4. Well, if it's going in the hub, it's going to hit everywhere. But when it comes over to the bridge is going to say, oh yeah, PC4, I know where that's at. It's actually sitting on this part of my bridge. So when that traffic comes in and hits this bridge, the bridge will take that traffic and forward out that interface. If I had another hub sitting here, and had a couple hundred more PCs sitting over here, same thing. This bridge will have the table of all these MAC addresses. So the bridge is a layer 2 device. And he will forward that traffic based on those MAC addresses. Now, this gives the bridge a very large table. And it gives him a big job. He's sitting in the middle saying, okay, I'm going to take all this information, I'm going to record all the MAC addresses, and I'm going to be this guy in the middle. So if you ever want to talk to this section of the network, you're going to have to come through me. So if the bridge fails for whatever reason, you know what I mean? Imagine that. This hub will lose connectivity to everyone. And so on and so on. You won't see, we're not going to be discussing bridges in that fashion. But I'm just giving you a definition of what they do. Repeaters is a concept of taking traffic that's coming in a interface, regenerating, making a copy of that data, and regenerating it and sending it down. We're not really regenerating. I mean, imagine voltage coming down. And let's say you start off with 5 volts. And by the time you get down here, you're like at 2 volts. You're almost dead. And you come into this device. The device says, okay, I'm going to take this data, I'm going to kill it, copy it, and then I'm going to send it on its way. And of course, when I go to resend it, I'm going to be sending it at what any device would be sending it at, 5 volts. So this is a concept of a repeater. People like to say we're regenerating it, but really we're just copying the data. We're closing this, copying it, and sending it back down as new traffic. That's the idea of a repeater. Because traffic can only go but so far before it starts losing its flow, its power, its oomph, so to speak. And of course, nodes, every one of these devices that have an IP address is a node. This is a node. That's a node. That's a node. That's a node. Make sense? And that's what all these devices are. A hub. Now, the reason why I drew that picture before was to give you an idea how they all connected. Because obviously, we're not going to have a layer 2 device sitting here on the edge of our network going into the cloud, right? I mean, it just makes no sense. It's just not going to happen. Unless the ISP offers a layer 2 solution to move your traffic. That's possible. But in our studies, we're not going to look at this ever in this fashion. Layer 3 routers sit on the edge of our networks and does routing. Anytime we're hitting a router, we're moving up to layer 3. So a hub is an interesting device here. And the reason why it's interesting, because it gives us the power to plug in multiple devices. This is way before probably you even thought about networking. When I got into IT, which was about 92, 90, maybe 94, something like that, I used hubs. I used to go to, CompUSA, not CompUSA, Computer City. And I used to buy hubs for my own personal network. And still back then, they were kind of expensive. Now, the idea was, originally when I was networking my PCs, and this is the sole purpose of playing games, this is how we had to do it. Just a cable between the two. It had to be a crossover cable. So knowing that it had to be a crossover cable and trying to figure that part out, that was really nerve-wracking for me back then. I didn't have any networking skills. I had PC skills back then, not networking. So I went out and decided that I wanted to network with just more than just one other PC. I wanted to network with my buddies. Now, eventually, I end up getting a cable splicer and creating these crossover cables going from PC 1 to PC 2. But when I wanted to network with my friends, I would create this hub. Not create it, I would go out and buy this hub. This gave me the ability to communicate with other PCs using straight through cables. And this is nice. Because obviously here, as we talked about before, pin 1 and 2 was transmitting, and on the hub, pin 1 and 2 was receiving. So I did not have to deal with crossover cables. I could just plug a straight cable through, the hub took care of the rest. The problem was, every time PC 1 had to send data to PC 2, 3 would have to get it. Every time. Every time. Now, PC 3 would look at that information, open it up and say, this is not for me, and it'll get rid of it. But that's still, PC3 still had to involve himself. And now that we have PC4 sitting here, he would have to start involving himself as well. Now, everything was fine until you started getting a lot of characters on the screen. Then you would start to have what we call this a lag. Now, I want you to think about it. If I have 100 guys on the screen that are walking, that's fine. Especially if you're playing the game and, you know, let's say this is, okay, let's say this is Kyle and this is Tim. On Tim's screen, he hasn't explored this land yet, so it's just darkness. But as soon as my characters start to come out of the darkness, and Tim can see it on his screen, well, now all these characters in their placements and where they're at, that data has to be sent to Tim. So Tim will know where my characters are on his screen. Otherwise, what would be the purpose of networking if whatever was happening on my screen wasn't happening on his? But imagine PC2 hasn't explored this land yet. So he's going to be getting all this 100 characters that I'm sending over to Tim, and really technically PC2 doesn't need it yet. Now this is just theory. I'm not telling you this is how gaming works. So all the bits and all the data that needs to go to PC3 is also hitting PC2. If I need to send data directly to PC3, 2 and 4 will always get it. And this is what caused what we would call a lag. Because the PCs were slowed down, not because they couldn't keep up, but because the hub's bandwidth was just overloaded with data. And so were their network cards. So the network cards were overwhelmed. Here's another issue we had, considering the fact that everyone gets all the data. When PC1 sends the data in, and PC2 sends the data in, and if they send at the exact same time, guess what happens? There's an interesting thing that we call half duplex. Imagine a walkie-talkie. When Kyle is sitting here, he's trying to talk to Tim, and they're sitting on channel 1. This is a frequency. And when Kyle speaks into here, he pushes this button, and this allows Tim to communicate. But this channel is a pretty interesting channel because when they're communicating across this channel, once Kyle pushes that button, this channel is occupied. Occupied meaning when I'm talking on this channel, no one else can be talking, and someone else needs to be listening. Now, if Tim wasn't on this channel, if he was on channel 2, obviously he wouldn't pick up that message. But if he's on channel 1 like he's supposed to be, he will hear me talk once that voice goes down the wire, or down the channel. And Tim picks it up. When Tim does this, though, he's going to wait until Kyle finishes speaking, then he's going to push the button, and then Tim will be able to speak. And now Tim is occupying the channel, and Kyle needs to listen. What happens if they push the button at the same time? They're both trying to access and occupy the channel, and guess what? They collide. And this collision makes it so Tim can't hear Kyle, Kyle can't hear Tim, but they're both speaking, but the information isn't getting through. This is why when you use this communication, you would let the person know on the other end that you were done by using the word over. So if you wanted Tim to pull the lever, you would say, Tim, pull the lever over. And that word over, when Tim heard that, meant that he was done communicating. So now Tim can use that channel. This is called half duplex. Only one person can speak at a time. And while someone's speaking, the other person can be listening. But if they try to talk at the same time, it collides and no one hears anything. And hubs work in half duplex. And that's a problem. So that means only one PC can communicate on that hub at a time. Very interesting. If A PC can only communicate at a time. What does this mean? There's this thing called CSMA CD, which means carry, sense, multi-access collision detection. I'll say it again. Carry, sense, multi-access collision detection. This is an Ethernet protocol that monitors how traffic works on segments. Now, when we say segments, we mean networks, or like we had before, we had a router coming into a switch and coming into our PCs. They all on the same subnet. This is our segment here. Subnet or segment. PC1 goes to communicate. He's listening on the wire. He's listening. And he's not going to try to do any transmitting unless there's nothing on the wire. And as soon as he knows that there's nothing on there being transmitted, bam, he starts sending. He starts sending his traffic, and he's good to go. Now, this is great because every PC on this segment or on this network are doing the same thing. Everyone's doing their job. They're waiting for a clear signal, and bam, then they send it out. But what happens if PC 1 and 2 both hear that clear, both listening and realize, oh, it's clear to transmit, and they both transmit it at the exact same time? Just like our walkie-talkies, they collide. Now, this is what we call a collision. When this collision happens, all the PCs on there will get this jam signal. CSMACD will send out this jam signal. And when everyone gets that jam, they're all like, okay, stop transmitting right now. Everyone stops transmitting. And then each one of them will get a random time. That random time will be milliseconds, seconds, however. So PC 1 might get 13. PC 2 will get 23. They'll all be random. And then the timer will start to click down. 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And now PC 1 will start to communicate again. And then PC 2, then 3, then 4. After theirs hit 0, they'll start transmitting. And that's the job of this, to stop that collision from happening. That's why we call it a collision detection, and we make action. We take action upon this and send out that jam signal. And this is what CSMACD does. It's an Ethernet protocol used to stop collisions when they occur. Does that mean we're going to have a collision again sometimes? Most likely, yes. The chances of that happening are very high. And this hub, when you used to buy it, used to have this little light. And every time this light would turn amber, you would know something was going on. Why? Because right underneath there, guess what it said? Collisions. And you could see the collisions. It would turn amber. And you would also know something was going weird if your collision light was blinking so fast, amber, that it just looked like it was on. Well, I mean, obviously we're having some type of collision, some big, huge collision issues. And I've had this happen with my hubs, and come to find out it was a bad hub. I went out and bought a new hub, and everything worked fine. The hub just wasn't doing its job. So because of this, this is kind of an annoyance. Destination MAC, same thing, sending the data back. Now, this is all great, but because we're on the same network here, our LAN is as far as our layer 2 can take us. Now, that's an interesting way of explaining it. This is my LAN. Can my LAN transfer over to here? No, it can't. Even though if this PC had the same had an IP address in the same network, these routers cannot have two interfaces in the same network. So this here is going to be in a whole different network. Now remember, It's forwarded by the layer 3 address, but it still has to build layer 3 and layer 2. And this router is only going to accept that information if the layer 2 information is its own. Now, you'll find that this might not be the case with layer 3 interfaces, but we'll find that out in the future when we actually do a lab. So this is how far this data goes. This is the distance of your LAN. Now, we call this the edge because this is as far out as it goes. And we call this the edge because this is as far out as it goes. So you have these two types of edges. So let's look at it from this perspective, doing it up and down. Here I have a router, router 1, that goes to the cloud. This is the edge of our network, our LAN network, right here. Because once this traffic hits this router, he's going to be sending that traffic beyond this network. See, originally, if this was a 192, we'll make this 192.168.1.1, and we'll make this PC 192.168.1.10. Now, let's think about this. He goes and he needs to send something outside of his network. He's going to send it to what? His default gateway, which is 1.1. Default gateway is 192.168.1.1. He's trying to communicate with a 192.200 address. So, when he sends this data out, his source IP is going to be 192.168.1.10. His destination IP is going to be 192.200.200.10. This is going to be his layer 3 information, which is layer 2. His source MAC is going to be 66:66, which is himself. His destination MAC is going to be, what was that again? That's right, the MAC address of the default gateway, which we'll just say it's we'll just say 11.11. So now, because we have the destination MAC address of 11.11, let's think about how this is in here. If this is a MAC address of 11.11, he goes to send data. This switch port here, which is port, we'll say port 10. In the MAC address table, he's going to have 11.11 belongs to port 10. Switch 1 is going to send that information over to switch 2. So from switch 2's perspective, he's going to say, okay, now this might be port 11 sitting here. From switch 2's perspective, he's going to say, in order for me to get to 11.11, I need to send this out port 11. PC3 is going to do the same thing in its MAC address table. So 3 is going to send that traffic down as well. Starting to see what's happening. As this data is coming down, these switches know how to get to this MAC address. So now, if I am going to be forwarding based on the destination of 11.11, that's going to go up to this switch as this data is going into this switch 6. Switch 6 is going to say, oh, 11.11, I have to send that out this port. That goes all the way up to switch 3. Switch 3 says, oh, 11.11, that needs to go out this port. Switch 1 says, oh, 11.11, that needs to go out what? This port. Switch 1 will send that traffic down, and switch 2 will see that data being sourced on this port, which that tells you can have more than one MAC address on a particular port. So if I have here, let's look at this. Switch PC1, we'll say it's 1, 1. 2 is 2, 2. This data goes into here. The first thing this switch is going to do is say, we'll say this is port 1, this is port 2, this is port 3, this is port 4, and this is port 11. So PC1 is going to send data out. This switch is going to say, okay, so I'm going to look at the source MAC address. I'm going to put it in my table. So MAC address of 1:1 equals port 1. And that's in this switch's database, in his MAC address table. Now, that traffic is trying to get somewhere. So what happens when that data needs to go up to here? It's going to leave this port. It's going to go up to this port. And this port's going to say, I got data coming in on this port. What's the MAC address? What's the source MAC? Oh, 1.1. So then that goes in this table. What port is this? We'll make this port 5. And he's going to say 1:1 equals port 5. So that means with these uplinks, if I have 10 PCs sitting here, that means this switch will know for those 10 devices, it's going to be in the MAC address table. So now when switch 2 gets any information for the 10 PCs sitting down here, he knows it needs to go through this port. That's why it's very crucial for the switch to look at the source MAC address at all times. And these tables are built based on the traffic that's coming through. But what about a broadcast? The first thing a PC does is sends out a broadcast. What's that broadcast? DHCP. Let's think about this broadcast. I need a DHCP server. That information comes through here. What does a switch do with a broadcast? Sends it on all ports except the one it came in on. The first thing switch 4 is going to do before he sends that broadcast, though, is look at what? The source MAC address. Puts it in a table. And if it goes out all ports when it came in on, what's it going to do? It's going to hit this port. First thing a switch is going to do is look at that source MAC address. And bam, goes in this table. Then he's going to send it out here. What's this switch going to do when it gets that broadcast? Bam. Put the 1.1 in his MAC address table, because the first thing he's going to do is look at the source. And then it's going to go out here, and then PC3 is going to get it, then it's going to go out here, PC6 is going to get it, and it's going to go out this port, and switch 1 is going to get it. Now, this is how they're building all their tables. So, when this is done, and PC3 wants to send that traffic coming up here, by the time it gets up here and hits this router, it's all been carried by the layer 2 information. Every decision from switch to switch was made by the destination MAC and its local table in each one of the switches. Wow, that's awesome. I never even had to look into layer 3 information. All done by layer 2. But once we get to this router is going to look at the destination MAC information and says, oh, that really is for me. I'm going to strip this off because I don't base my decisioning on that. I'm opening it because it's for me. Oh, there's some layer 3 information here. Source and destination IP. 200 to 200. Oh, well, that goes out this interface. Let me send it out here. And, of course, he's going to rebuild the source and destination IP addresses, keep them the same, and then rebuild or rebuild the source MAC and destination with the proper source and destination MAC addresses. Your local area network goes as far as the edge of your network. So let's define some edges here. Obviously, where I'm marked here is my first edge. That's one edge. That means past this router, you're no longer on my network. You're no longer on my subnet. So now, where else do we have an edge? Here. Here's an edge. Because past this PC, there's nothing else. That's it. Which means also, this switch is considered the edge of our switch network, and this will be the edge of our switch network. If we wanted to say, okay, what's the edge of our switch network? These will be the edges, because that's as far as the switches goes. If you want to consider them as hops, you could say 1, 2 hops away this way, 1, 2 hops of this way, and 1, 2 hops this way. But our edge of our network means that we go no farther. And that's what our edge means. So your LAN goes as far as your layer 2 information can carry you. That's the best way to explain it. My layer 2 from PC3, that my layer 2 information can carry me to the edge of this router. It can also carry me up to this switch, up to switch 2, up to switch 4, down to PC 1, PC 2, PC 3, which is itself, and up to switch 3. There's the size of my LAN right there. That means PC 3 can travel this way, can travel this way, can travel this way, can travel this way, and can travel this way. And that's how far our LAN can go. IEEE. IEEE is an organization called Institute of Electrical and Electronic Engineers. That is what IEEE is. They are just an organization that sets standards for protocols, which means if you want a protocol to be a standard, this organization will be one of the ones most likely you want to deal with. If you want to implement a protocol or use a particular protocol in your device, let's say I want to build Kyle Incorporated routers, then there's certain standards that I would have to follow. Well, this will be a good place to start. Talk to them and say, hey, I want to run OSPF on my device. IEEE says, okay, well, you have to follow these standards. Does that mean that's exactly what's going to happen? No. I'm just trying to tell you that the IEEE has certain standards, and if you follow these standards, you will be an IEEE number. So, spanning tree. Spanning tree has an 802.1d standard. This is an IEEE number, but it's just an organization, and you're going to hear it a lot in the networking world. So let's talk about the data link here, the data link layer. The data link layer is your layer 2 layer. Because notice that we have the physical, and then we have the data link layer, which is sitting right on top of that, which is my layer 2. Then we have my network layer, which is layer 3. We say layer 3 and layer 2 all the time, but we're not really calling them by their real names. The data link layer is layer 2. Data link provides reliable communication over the media. Well, that's awfully vague. Ethernet divides the data link into two sections, LLC and MAC. Okay, well, MAC makes sense. We talked about MAC addresses. But this LLC, what is that? It's called Link Logical Control. Now, the Link Logical Control layer, which is a layer within layer 2, controls frame synchronization, flow control, and error checking. That's it. Is this something that you interact with? No. Is this something that you need to know? I mean, yes, for your exam. Flow control is the ability of controlling the flow from one network card to another. Notice that we have the keyword logical, which means this will be a logical connection between two devices. And we're talking about the link. So when we talk about the link, that means obviously we're talking about the connection between one network card and another network card. And here's our physical link. But we're going to have these logical sessions between these network cards. And something has to control this logical link that we have between the two network cards. And that logical link will be controlled by the LLC. And the LLC will have frame synchronization. It will control the flow, or we should say the speed, making sure that we have the right amount of speed between the two, so one's not getting the speed or getting the data too fast, backing up, dropping frames, stuff like that. And error checking, making sure that when we leave the data from this side, it's not corrupted by the time it gets on this side. It acts as an interface between media access control. Media access control. Oh, MAC addresses. And it acts as an interface between the network layer and the MAC address. Okay. Do I really know in detail what that is? You can find out. All depends on how deep you want to go. It provides multiplexing. We talked about multiplexing, being able to have different medias and use port numbers to define those medias, or different protocols. I'm sorry, different protocols going across the same media. It provides multiplexing mechanisms so protocols to be transported over the same network media, and can also provide flow control mechanisms. Determines when a device can send data over the media. CSMA CD. Carry, Sense, Multi-Access Collision Detection. Well, there you go. Now you know where CSMA CD sits. It sits at layer 2. Guys, that's what the data link does. When you start reading about the data link, it just gets so confusing because you're like, wait a minute, we got the link logical control and the MAC addresses. What's going to happen is you're going to be focused on the MAC addresses. You're going to be focused on the link logical control. Seriously. This is all you're going to really be focusing on. And eventually this is going to go on the back burner. But just have an understanding of what the link logical control is. Ethernet. Notice we're getting in all these terms and definitions now. We talked about IEEE, the data link layer, and Ethernet. I like talking about these separately because these are one of the most 3 confusing things ever when people start reading about it, because it goes into so much detail to a level of too much detail. And you're just like, I really don't know what this does. Ethernet is a set of standard rules. Wow. What's a set of rules? It's a protocol. Ethernet is just rules. Whose rules? Not your rules, not my rules. These are not rules you manipulate. They're not rules you go in and configure. These are rules set by IEEE that must be followed if you want to communicate with other Ethernets. So Ethernet is a set of standard rules that software and hardware devices will use for creating communication for local area networks. Well, isn't this of this? This is kind of an annoyance on how our traffic is moving. And we might want to have a better way to do this. Now, this is how the hub works. So let's talk about how a switch works. Because one of the things that we have an issue with is all these collisions. Collisions causes what? When the jam signal goes out, we have to wait for those PCs to do their thing. If collisions are consistently happening, there's always going to be jam messages going out. And this is going to cause us issues. So the word went out that we need something better, right? And still having a hub just send traffic to everyone, which means when it goes into this port, if this is a 24 port hub, it's going to go to all 23 ports. Someone said, well, what if we design a mechanism that allows us to only send communication where it needs to go to? And this is where we have a switch. Imagine that when PC 1 needs to communicate with PC 3, that traffic only goes to PC 3. Now that sounds like a dream, but that's exactly what happens. With this method here, we have the ability to send traffic in, and based on the MAC address that we're sending it to, we're going to forward that data to that particular PC. Now we do this by ports. Now these ports are going to be configured automatically to record the MAC addresses. So when PC 1 sends data in, and everyone's MAC address is going to be 1111, this is going to be 2222, 3333, makes it easier, 4444. When this PC sends data into switch 1, immediately what that switch does, every time that data comes in here, he's going to say, let me look at the source MAC address. Because remember, what did I tell you? We're going to have the source IP, the destination IP, right? And that's going to be my layer 3 information. But then my layer 2 is going to be what? Source MAC and destination MAC. So when PC1 sends its data into that switch is going to say, let me look at the source MAC address. Let me look at this. Oh, the source MAC address is 1111. Let me go and make sure that this is in my table. What table? The MAC address table. Sometimes you hear it called the CAM table, but I call it the MAC address table. And in that MAC address table, we have the MAC and the port number. So we'll say this is port 1, this is port 2, this is port 3, and this is port 4. So when the switch looks at that data that's coming in and says, well, 11's not in my table. Well, let's add it. 1111, that belongs to port number 1. Now, he's trying to send this data to 2222. Well, guess what? 2222 is not in its MAC address table. Everything is based off this MAC address table. So when I'm going to need to send data to 2222, I am going to look at my MAC address table to find out where that needs to be sent. Well, it's not in my table. Well, how do I fix this problem? I got to find out where it's at. So I'm going to send out a broadcast message. Anytime switch gets data coming in and it needs to send a broadcast, it will send a broadcast to every port except the one it came in on. This will happen with broadcast and multicast. So the switch, if he has an unknown MAC address, that's what we call it, an unknown MAC address. It's unknown because we don't know where this MAC address lies. We don't have a clue. So we need to find out. So we're going to send out a broadcast. I'm not going to just drop the information. I'm going to send out a broadcast. So it goes out every port. So PC2 is going to get it. PC3, PC4 is going to get it. But the traffic is really meant for PC2. This message that's going out is saying, hey, this is a broadcast. So then we're going to change this information to be all Fs, send it out. PC2 would get it because it's a broadcast message. He's going to open it up. He's going to see that it's sourced from 1.1. And he's going to look at the source IP address and the destination IP address. And he's going to say, well, that's for me. All right, let me go ahead and take care of that. And when he goes to send information back to PC1, well, guess what happens? He builds his source IP, his destination IP, and then his source MAC and destination MAC. He got the source MAC from himself, which is 2222, and he got the destination MAC from when the data was sent from PC1, which is 1111. Now this data goes into the switch, and the switch immediately looks at the source and says, wait a minute, 2222 is not in my MAC address table. Let me add it. That's in port 2. And then he says, well, let me look at the destination MAC. 1111. Oh, wait a minute. Let me look at my table. Oh, that is in there. Let me send this data to port 1. And port 1 only. Notice I said port 1 only. So originally 3 and 4 got the broadcast, but once this table is built and the switch knows everyone is on the ports, guess what? Everyone can now communicate with each other, and when PC1 wants to communicate with PC2, it only goes to 2. 3 and 4 will never know what PC1 is sending to PC2. Much better than a hub, wouldn't you say? Now, because of all this, this gives us the ability to lower our bandwidth going to other network cards. So imagine having this PC that I had before, and we were doing my gaming. And I remember I had this, like, you know, this fog of war here, and people couldn't see it. But then all of a sudden my 100-some guys comes on the screen, and I'm on PC1, and PC2 has this area of the map exposed. So that data only needs to go to PC2. PC3 and 4 hasn't explored this area yet. So to its perspective, it's still, those 100 PCs haven't come out yet. Or those 100 characters haven't come out yet. So now, only PC2 needs to get all that data. It doesn't need to go to all of them. Might be a poor analogy, and I apologize for that, but you get the idea. It's either my 100 guys on a game machine, or it's talking about boring application data. I like to talk about games. Okay? Now, this makes it very powerful, because I know now that I have this ability to send data into this port and get right over to port 2. Now, another interesting thing that a switch provides for me is this thing that's called full duplex. Now, before we talked about half duplex. What does full mean? Imagine having a channel just for transmitting and a channel just for receiving. Imagine that. Isn't that what a telephone's like? Aha. A telephone is like that. Where with the walkie-talkies, you can actually think of the walkie-talkies as, you know, as we had these channels going over to the antenna. You can actually think of these antennas as a single cable. But if I had another cable, here's cable 1, here's cable 2, then both of us could push the button, because anytime he is going to push the button, he's going to be talking on this channel, and be receiving it on this end, and whenever he hits the button, he's going to be transmitting on this channel. Oh, interesting. So instead of having our transmit receive on the same channel, one side is going to be transmitting whenever he pushes the button, and the other side of that channel on his end will be receiving. And vice versa. Well, that's good to know, because now we both can push the button and we can overtalk to each other. So when Kyle is sitting over here talking to Tim, Tim could be saying, hey, Kyle, go ahead and pull the lever. And as he goes to pull the lever and Kyle says, okay, I'm pulling the lever, in the middle of that, Tim could say, wait, don't do anything. Stop. Even though Kyle has his hand on the button. I would say that's much better, wouldn't you? So switches have this interesting thing called full duplex, which is just like a telephone. You and your girlfriend can be arguing for days on the telephone, back and forth, and you don't have to keep using the word over. So now this PC has the ability to send data and receive data at the same time. Now this is nice, because before, when we had our hub had everyone on this same collision platform. There's PC1. I'm just going to draw boxes this time. PC3. PC4. PC1 sends data in, which means if PC3 or 4 or 2 send data at the same time, it collides. Which means 2 can collide with 3, 4, and 1. 1 can collide with 3, 4, and 2. 4 can collide with 2, 3, and 1. Does that make sense? So this hub and all these devices are in one big, what we call a collision domain. We're in one big collision domain, because these PCs can collide with each other. And this is a problem. So now, think about our full duplex. Because over here, we can only communicate one at a time. If anyone else is communicating, we're colliding. With a switch, it gives us the ability to have those multiple channels to transmit and receive at the same time. So now, guess what? If this data goes into this switch port and does not go to everyone, it only goes to the port that it needs to go to, and it's only forwarded based on the MAC addresses that have been found on those ports, I I'm not going to have the ability to collide with 3, 4, or even 2. Oh, this is pretty awesome, because now, how far does my collision domain go here? From the switch to the PC. And you have to ask yourself, where can I really have a collision? Really? Because if I'm transmitting on this channel and receiving on this channel, how will they ever collide? Where in our half duplex, I can transmit and I can transmit, but I'll be doing it on the same channel, and once they meet, boom, they explode or collide. So my collision domain is per port, and that's what makes it wonderful. So what's the key factor of learning about a switch? It uses MAC addresses to do its forwarding decision. It'll also send out broadcast messages if I have them all set to FFs. As my MAC address is my destination MAC address, it will send those out as a broadcast. It goes out all ports except the one it came in on. Also, if I have an unknown destination MAC address, if I have that, that means I have to send on a broadcast. It'll go out, and what does the broadcast do? Again, all ports except the one it came in on. So this is awesome. So what did we learn about a switch? 1, the second the data comes into a switch port, it checks the source. Every time that data comes in, it checks the source MAC address of the layer 2 header. If that information is not in the MAC address table, it puts it in there. Now that's nice to know, because if I take PC off of port 1 and plug it into port 10, what's going to happen? In the MAC address table, it will see that 1111 belongs to port 1. But the second that this PC is plugged into port 10 and starts sending data out, the switch is going to see that MAC address 1111 is coming in on port 10. And what is he going to do immediately? He's going to remove it from 1 of the table and put it in port 10. So this whole entry will be removed with the port 1, and he'll put a new entry in for port 10. Okay, does that make sense? Port 1's entries will be removed, port 10 will be added. And this is constantly happening. So that gives you the ability to plug in devices anytime you want. The switch will do its job. He will record that MAC address. Now, based on the fact that I'm plugged into switch port 10, anytime PC needs to communicate with PC1, that data comes into this switch port. Switch looks at the data coming in on port 3, looks at the source MAC address, says 3333 is not in the table. Let's put it in there on port 3. And let's look at the destination. Destination is 1111. Oh, well, that's already in my table, so I'm just going to forward that data out port 10. No actions needed, just forward it. All based on MAC addresses. And that's the beauty of a switch. And that's the power of the switch. So that's pretty much all our devices, our LAN devices. So let's talk about our distance. How far does a LAN really go? Where does it end? Well, that's pretty interesting. Let's take a look at this. Here's a PC. PC1. Going into switch 1. We're going to say it's on the 192.168.1.0 network. This is PC1 here. So here's my network number, here's my network number, here's my network number, and this is a host number. Now, obviously 0 can't be a host, so we'll just turn this into... Now, 0 can't be a host for this particular network. You will be able to see that there's zeros and IP addresses later on. Now, because of this, PC1 has an IP address and a MAC address. In order for him to communicate with this router also has to have an IP address and a MAC address. Otherwise, he will not be able to communicate. Now, if PC1 pings PC2, or router 1, we know what's going to happen. The first thing that's going to happen is he's going to build his layer 3, he's going to build his layer 2, and he's going to send it on. Source IP, destination IP, source MAC, destination MAC. That gets sent out. He gets the MAC address information for himself, the destination MAC address he gets from his ARP table. That hits the switch. Now the switch looks at the source MAC, finds out if it's in the MAC address table, adds it in the MAC address table if it's not there, then looks at the destination MAC address, and then forwards it on based on the MAC address table. Which means if your MAC address table is incorrectly, it will go out the wrong port with no hesitation. So now this data is going out this port, hits the router gets it, and he responds to the ping. And he does the exact same thing PC had to do. He has to build a layer 3, has to build a layer 2, has to look at his ARC table for the destination MAC. Same thing, sending the data back. Communication for local area networks. Well, isn't that nice to know? It's as simple as that. It took me a long time to find a simple definition. You'd be surprised how many definitions of Ethernet are out there. This was the simplest one that made sense. It's just a set of standards, standard rules. That's all. If you want to talk on the Ethernet with other people who are on Ethernet, have the same rules as they do, and you guys will be able to communicate just fine. Don't have the same rules, you're not going to be able to communicate. The other devices will just drop the traffic. Or you won't be able to even read the traffic that's coming to you, either or. Domains and collision domains. So when you saw my diagram that we had before with the 6 switches, a broadcast, what does a switch do with a broadcast? It sends it out all ports except the one it came in on. Now, if that's what a broadcast message does, let's think about this. A router will never forward a broadcast message. It never will. But the router will get the broadcast messages. So if the router will get the broadcast messages and never forwards them on, that means this is pretty much the edge of your broadcast. And since a switch will forward a broadcast out every port, how far does that broadcast go? That will come into here, go out this port, go out this port, go out this port. And these are PCs, so these are the edge of your network as well. So this is where you have your broadcast domain. We call it a broadcast domain because when this PC1, sends a broadcast, the distance that the broadcast will travel is your domain. That broadcast will come through up to this PC, up through here, up to here, and up to this router. And then the router will not forward it. So this router, when you put a router in place, you really are stopping that broadcast traffic from going any farther. Now, we already learned that our collisions domains are really from the switch port to the PC. That's great, because there's no point in even having CSMA-CD anymore, considering the fact that we have full duplex going on, and our collisions are only to the switch port out to the edge device. Now, this, again, is another broadcast domain. As you can see, broadcast comes out from this PC. It's definitely going to go out this one. A broadcast, what does the switch do with a broadcast? Sends it out every port except the one it came in on, and then it'll stop right here at the router. So this is another broadcast domain. This is the same thing, no difference. This is a hub, so it doesn't really matter what type of message it is, because a hub sends traffic to all ports anyway, whether it's a broadcast or not. It's just a layer 1 device. It makes no forwarding decisions. It just sends it out to everyone. It's just like taking all the wires and just bundling them together. So this broadcast message is just definitely going to go here, and there we go. Now, the only difference that we have to worry about here, besides the broadcast domain, is our collision domain. With a switch, each one of these switch ports are its own collision domain. So that means even this switch port going to this router, it's its own collision domain. So right now, if we counted these collisions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have 10 so far. But what about this one down here? Because we have a hub sitting down here. And if we have a hub sitting down here, this is going to act a little different. Because, remember, this isn't a switch port. This is half duplex. It's a hub, so it's half duplex. And if when PC1 sits over here and brings that data in, guess what? It's going to all of them, no matter what the data is. So if any one of these communicate at the same time, it will collide within this hub. That makes this hub and everything that connects to it, notice what I said. This makes this hub and everything that connects to it its own collision domain. So here we have, because these are switches, switch 1, switch 2. We have one collision here, we got 2, we got 3, we got 4, we got 5, we got 6, we got 7, we got 8, we got 9, we have 10, and we have 11. So all in all, we have 11 collisions domain. This PC, and this PC is all on one collision domain, including this router's interface. This you need to know. You need to know the difference between a broadcast and a collision domain, and you should be able to get a diagram like this and recognize what is a collision and what is a broadcast domain, and be able to answer the question, how many collision domains and how many broadcast domains are there. Now, we saw these values as far as our MAC addresses, and we see that they're actually these weird numbers. MAC addresses have different names. They're called layer 2 addresses, Ethernet addresses, physical addresses, burnt-in addresses, and hardware addresses. Now, our burnt-in addresses can also say BAI. Each one of these MAC addresses have 12 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each one of these numbers can have a value of 0 to 9 or A through F. The reason why we go from A to F is because each one of these places has the possibility of 15, a value of 15. 0 through 15. So let's write this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, this is pretty easy. Don't forget our 0 here. This is pretty easy because 0 through 9 are going to match up. But I only have one place to put this digit. I can't write the number 10 as 10. I can't do that because I only have one place. So now, my 10 and my 11 and my 12, 13, 14, and 15 becomes A, B, C, D, E, F. And that's why you will see a mixture of numbers and letters in a MAC address. Later on, when you learn the conversions of hexadecimal, because that's what this is called, hexadecimal to binary, you'll understand why these values are the way they are. And you'll start to understand the binary system, and then hexadecimal, when you learn to convert them, it'll make sense. We say that it's 48 bits, which means if it's 48 bits and there's 12 numbers here, what's 12 divided into 48? That's 4, right? That's 8 and 4. So that means each one of these numbers have 4 bits in them. Now, MAC addresses are assigned automatically. You can change the MAC address numbers, but you're not changing the real number. You're just overlapping it with a logical number. Which means if this is the MAC address on here, and I put a MAC address of all ones on that MAC address, this is still the real MAC address. You can never change this number. This is hard-coded onto the network card. But the first 6 numbers, or first 6 digits of this number, is assigned by an organization called the OUI. The OUI, which is this number here, the OUI number, are these first 6 digits. So I'm Kyle Incorporated, and I call up the OUI and say, hey, guys, I want to make network cards. I want to manufacture them. They say, sure, no problem. Your number is 238490. And I say, thank you very much. And every one of my network cards must start with these first 6 digits. It must. And guess how I'm going to make my network cards? When I make my first one, it's going to be 000001. My next one's going to be 02. My next one's going to be 03. That means I made 3 network cards now. Now I'm going to get to number 9. 09. What's my 10th one's going to be? 0A. 0B. And then eventually I'm going to get up to 0F. Now, after this, what do you think the next one's going to be? You guessed it. 10, 11, 12, all the way down to 19, all the way down to 1A, all the way down to 1F, and then guess what the next one is? 20. See how that's going? And eventually I'm going to get all the way up to 9F. And what do you think the next one's going to be after 9F? It's going to be A0. Because this will be my 10th place, and this will drop back down to 0. Just like counting numbers, you're just using a hexadecimal. And eventually I'm going to get all the way up to EF. And what do you think the next one's going to be? F0. And then eventually that's going to go all the way up to FF. Let's take a look at our MAC address now. So here we go. Here's a MAC address. 00OC29. That's really the first number I'm looking for. I'm going to go ahead and copy that by right-clicking on it. And I'm going to say MAC address lookup. Just go right to here. OOCC 00OC29. Let's look it up. Well, check that out. VMware Incorporated. Well, now I know this is a MAC address or a network card that has a MAC address off of what? VMware. Now I know this is a VM machine. Wouldn't that be helpful? Because I'm going to tell you, VMs are kind of hard to track down when you're on a network. So here's my personal machine. Let's find out what we have here. And MAC address, I just want the first 3. Oh, that's right, I can't copy it. So that's 00. Oh, actually, I can copy it because I'm on my PCs now. There we go. 002618. ASUS computers. Now I know that I have an ASUS board. Well, at least, well, not really an ASUS motherboard, but an ASUS network card. Considering the fact that this is my own board card, most likely I have an ASUS motherboard. But nonetheless, that's how you use that tool. And it's just online, that's all. And that pretty much ends our network fundamentals. There's a lot of things you should be reviewing at this stage before you move on to the switch. Really, the major things that I want you to understand as we go back through here is obviously what a network is. Anything that is communicating that has an IP address is a network device. As long as you have more than one device on a particular media of some sort, whether it's physical, whether it's wireless or radio waves, as long as more than one PC are trying to communicate, you have a network. Obviously, you want to know that you're working on routers and switches, and that's all you're going to be doing with the CCNA routing and switching. These are only 2 devices you're going to work on. You want to understand your cable types if you're going to be getting a lab, which is your WIC 1T, your WIC 2Ts, what kind of cables you need to have, which is your DCE, DTE cables. your, if you want to use fiber between your devices, make sure you get the right SFP. You definitely need a console cable. Obviously, know what your network symbols are. Obviously, you want to know how it fits. You know, you want to know where a switch will lie in your network, where a router, when you actually need a router. Ethernet, we talked about that a couple times. It's nice to know what you're definitely what these mean. We talked about this is your speed, your 10 megabits per second, and that's up to 10. Saying that now it's 10 base, and we're using twisted pair. Got your cable types, which is your Ethernet, your Giga Ethernet, Fast Ethernet, which that's what this is. This is Fast Ethernet because it's 100 megabits per second. Your pinouts of your cables, crossover cables isn't really necessary to really understand the pins. I personally would. I would definitely memorize that 1 and 2 and 3 and 6 are transmitting. As part of your communication, and 1 and 2 are transmitting, and 3 and 6 are not. 3 and 6 are receiving. I would definitely commit that to memory just for your field purposes when you're at work. You never know, especially when you're on the knock. You never know who will be your site support. Know where your devices sit. At what layer? Routers are layer 3. Switches are layer 2. Hubs are not layer 2. They're layer 1. However, there's lots of people that say it's at layer 2 because it's on an Ethernet segment. And network cards are layer 3. And bridges are layer 2. Understand what an IP address is. The fact that it's made up of 4 numbers. Understand what your MAC address is. Understand that it's made up of 12 numbers. This is how your PC will read them or display them. This is how Cisco displays them. There'll be 4 numbers in each section separated by 2 dots. In Chapter 2, we talked about the OSI model. And I think we've done this heavily enough for you to understand what's layer 2 and what's layer 3. We talked about the OSI communication. We talked about how our PC builds those layers for every bit of communication going out. So remember, if I need to send 10 packets, I need to do this 10 times. It's not just once and then we're finished. It's for every piece of data that goes out. If you're using TCP/IP, TCP for your communication, you're going to be using layer 4 as well. And getting sequence numbers and acknowledgement numbers back. We compared the OSI model to the TCP model. We talked about TCP/IP, the application suite. We definitely talked about the 3-way handshake. We talked about the header of the TCP, the UDP header. We definitely talked about windowing. Talked about our sequence numbers plus our windowing. We talked about multiplexing a little bit. Definitely talked about port numbers. Definitely talked about communication types, which is our unicast, multicast, anycast, and broadcast. We talked about our communication basics, which got kind of complicated, even though it's basic. We never really went through the flow chart down here, which really isn't necessary. I usually do this for my classes. And we talked about our network types, our LAN devices and where they fit, how far our LAN goes. Talked about IEEE, the data link layer, Ethernet, carry sense multi-access collision detection, our broadcast and collision domains, and our basic formats of MAC addresses. And guys, that's it for network fundamentals.